How many children were lost before anyone thought to ask why? Not to war, not to plague, not to famine, but to something hidden inside the very body meant to protect them. There are graveyards scattered across Europe, small ones tucked behind village churches, where the stones are too small and too many, where the same family name appears again and again beside dates that never reach a first birthday. No one carved an explanation into that stone. No one could. The reason was circulating silently in their mother's veins, and it would take the world another few centuries to find the language for it. So before you let yourself sink deeper into wherever you are right now, before the weight of the day finishes leaving your shoulders, take a moment, like this video and subscribe, but only if you genuinely feel drawn to what we're building here. And wherever you are listening from, share it. Tell us your city, your time zone, the hour on your clock. It is always strange and beautiful to know that someone in Tokyo at dawn and someone in Buenos Aires at midnight are following the same thread of forgotten history at the same moment, connected by curiosity and the quiet dark. Now, let us go back, far back, before blood types had names, before laboratories existed, before anyone understood that the red liquid spilling from a wound was not simply life escaping, but a chemical archive carrying information about identity, inheritance, and incompatibility. For most of recorded civilization, blood was a symbol before it was a substance. It meant courage, lineage, sacrifice, guilt. It sealed covenants and stained altars. Poets compared it to wine. Priests called it sacred. Philosophers debated whether it carried the soul or merely served the heart. But no one, not the Egyptian embalmers who drained it with meticulous care, not the Greek physicians who believed it was one of 4 humours governing temperament, not the medieval barber surgeons who opened veins to release disease, none of them suspected that blood could be classified, that one person's blood might be fundamentally incompatible with another's, that a mother's blood might declare war on the child growing inside her, that ignorance had consequences measured not in academic papers but in coffins, small coffins, across centuries, in villages and cities alike. A pattern repeated itself so often it became invisible. A woman would give birth to a healthy first child, strong lungs, good colour, a baby that thrived. Then the second pregnancy would end differently. The infant would arrive yellow, swollen, struggling to breathe. Sometimes it lived a few hours, sometimes a few days, rarely longer. The third pregnancy, if it came, was often worse, stillborn, or born alive but failing so quickly that the midwife would not even hand the child to its mother, knowing the weight of that gesture when the outcome was already written. In the parish records of rural England, France, Spain, you can trace these patterns if you know what to look for. A family with 7 pregnancies and 2 surviving children, another with 5 pregnancies and 1. The records do not say why. They say fever, they say weakness, they say God's will. Occasionally a priest would note that the infant was born with a yellow pallor, a detail that meant nothing in the 17th century but means everything now. That yellow was jaundice, not the ordinary newborn jaundice that clears in a week, but the deep, devastating jaundice of hemolytic disease. Red blood cells being destroyed faster than the tiny body could replace them. Bilirubin flooding the system, staining the skin, damaging the brain if the child survived long enough for the damage to matter. No one connected these deaths. Each loss was isolated, private, absorbed into the enormous ocean of infant mortality that characterized human existence before modern medicine. Children died. That was the world. 1 in 3 infants in early modern Europe did not survive to their 5th birthday, and the causes were so numerous: infection, malnutrition, birth complications, diarrheal disease, that the specific pattern of healthy first child followed by dying second and third children dissolved into the general catastrophe. But it was there. It had always been there, hidden in plain sight, in every population where Rh-negative and Rh-positive blood coexisted, which, as it turned out, meant primarily in Europe, in parts of the Middle East, in scattered communities across North Africa, Populations where roughly 15% of women carried a blood type that would, under specific circumstances, turn their own immune system into a weapon aimed at their unborn child. The mothers bore the grief. They also bore the blame. In communities governed by superstition and religious certainty, a woman who repeatedly lost children was suspect. Perhaps she had sinned. Perhaps she had been cursed. Perhaps her womb was hostile by nature, a phrase that medieval midwifery texts actually used, though they meant it metaphorically, not immunologically. In parts of rural France, a woman who lost 3 or more infants in succession might be taken to a healing well or a saint's shrine, her body washed in cold water, prayers recited over her belly, as if the problem was spiritual contamination rather than antigen incompatibility. In German-speaking regions, there were folk beliefs about Wechselkinder, changeling children, infants who seemed healthy at birth but faded quickly, as if something had been exchanged, as if the real child had been taken and a failing copy left in its place. These stories might carry, buried deep beneath the myth, a faint echo of Rh disease, a baby that looked normal at first, then deteriorated within days as maternal antibodies destroyed its red blood cells. None of this was understood. None of it could be. The conceptual framework simply did not exist. Blood was blood. It came in one kind. It was hot or cold, thick or thin, according to the humoral theories inherited from Galen and Hippocrates. The idea that blood might carry invisible markers, proteins on the surface of cells too small to see, was not just unknown. It was unthinkable. The microscope existed by the 17th century, but even early microscopists like Antony van Leeuwenhoek, who first observed red blood cells in 1674, saw only shapes, tiny round discs floating in fluid. He could describe their form, he could not read their surface. The molecular landscape of those cells, the antigens, the proteins, the receptors that would eventually reveal the Rh system, was locked behind centuries of technology that had not yet been invented. And so the dying continued. Generation after generation, a woman in a medieval village buries her second child, then her third, and there is no one to tell her that her body is not broken, not cursed, not punished. That what is happening inside her is a precise and terrible immunological event triggered by a protein her blood does not recognize. That the child she lost was attacked not by demons or sin, but by antibodies, molecules her own body manufactured in response to a perceived invasion that was in reality her own baby's blood. The silence around this tragedy was not a conspiracy. It was simply the shape of ignorance in an era when the tools to see the truth had not yet been forged. But silence, whatever its cause, has the same effect. It erases. It makes suffering invisible. It allows patterns to repeat without recognition, without intervention, without memory. And when the truth finally does emerge, when the tools arrive and the molecules are named and the mechanism is mapped, the silence has already done its work. The dead are uncounted. The grief is unrecorded. The mothers who carried the evidence in their own blood are gone, and their stories went with them. What remains are the parish records, the small headstones, the folk tales of cursed wombs and stolen children, and beneath all of it, running through the centuries like a river no one could see, a protein, a single protein on the surface of a red blood cell, present in some, absent in others, a difference so small it took humanity thousands of years to detect, and so devastating that once detected, it would rewrite the rules of pregnancy, transfusion, and the meaning of compatibility itself. But long before that rewriting began, there was another silence. Older, deeper, built into the very foundations of Western medicine. A silence about what blood actually was, what it did, and what it meant. Because before anyone could solve the mystery of Rh, they first had to overcome something even more difficult. 20 centuries of being wrong about blood itself. For more than 1,500 years, the Western world understood blood through the lens of a single man who'd been dead since the 2nd century. Claudius Galen, physician to Roman gladiators and emperors, built a model of the human body so elegant and so authoritative that questioning it was not merely unfashionable, it was, at various points in history, heretical. Galen taught that blood was manufactured in the liver from food, that it flowed outward through the veins like a tide, consumed by the organs it nourished, never returning. The heart was not a pump but a furnace, heating the blood and mixing it with pneuma, a vital spirit drawn in through the lungs. There were 4 humours: blood, phlegm, yellow bile, black bile. Health was balance, disease was imbalance, and blood, the most important humour, was the essence of vitality itself. This was not ignorance in the way we typically imagine it. Galen was brilliant. His anatomical observations, drawn from dissecting monkeys and pigs because Roman law forbade human dissection, were remarkably detailed for their era. He identified major blood vessels. He described the chambers of the heart. He understood that arteries and veins carried different substances. But he built his system on inference rather than experiment, on philosophical reasoning rather than empirical testing. And once the system was built, it calcified. The Catholic Church adopted Galenic medicine as compatible with its theology. The 4 humours mapped neatly onto 4 elements, 4 seasons, 4 temperaments. To challenge Galen was to challenge the order of creation itself. So for century after century, physicians bled their patients. They opened veins to release corrupted blood, to cool fevers, to calm madness, to restore balance. They bled pregnant women. They bled infants. They bled the dying. George Washington, in 1799, was drained of nearly half his blood volume in the final hours of his life by physicians who believed they were saving him. The treatment almost certainly hastened his death, but no one questioned it. Blood was meant to be released when it was bad. This was settled science. This was Galen. The first cracks appeared not in theory, but in desperation. In January 1667, a French physician named Jean-Baptiste Denis performed what is considered the first well-documented blood transfusion into a human being. His patient was a 15-year-old boy who had been bled repeatedly by other doctors, 20 times in a span of months, and was near death from the treatment meant to cure him. Denis, working from a radical hypothesis that fresh blood might restore what bloodletting had stolen, transfused lamb's blood into the boy's veins. The boy survived. Denis was elated. He performed the procedure again on other patients, using blood from calves and lambs, sometimes with success, sometimes with catastrophe. One patient, a man named Antoine Mauroy, received 2 transfusions of calf blood. After the second, he developed violent tremors, back pain, dark urine, and died shortly afterward. His wife accused Denis of murder. The ensuing trial, though it ultimately acquitted Denis, led to a near-total ban on blood transfusion in France and eventually across most of Europe. The practice did not resume seriously for another 150 years. When it did, in early 19th century England, the pioneer was James Blundell, an obstetrician haunted by the women who bled to death in his care during childbirth. Blundell reasoned that if blood loss was killing them, then replacing blood was the logical remedy. Crucially, he argued that only human blood should be used, that the disasters of Denis's era were caused by species incompatibility. He was right about that as far as it went. Between 1825 and 1830, Blundell performed approximately 10 transfusions using blood from human donors. Some patients recovered miraculously. Others died in agony, their bodies convulsing, their skin turning yellow, their urine running black. Blundell documented these failures with meticulous honesty, but could not explain them. The blood was human. The donors were healthy. Why did some transfusions heal and others kill? The answer was sitting inside the red blood cells themselves, written in a molecular language that no one in 1830 had the tools to read. Each cell carried surface proteins, antigens, that functioned like identity markers. When blood from one person entered another person's body, the recipient's immune system checked those markers. If they matched, the blood was accepted. If they did not, the immune system attacked. The foreign red blood cells were destroyed, lost, releasing their contents into the bloodstream, overwhelming the kidneys, triggering shock, sometimes death. This process, hemolysis, was the mechanism behind every failed transfusion in history. But naming it, understanding it, required a conceptual revolution that would not arrive for another 70 years. When it finally came, it came quietly. In 1901, in a laboratory at the University of Vienna, a young pathologist named Karl Landsteiner performed an experiment so simple it seems almost impossible that no one had tried it before. He drew blood from himself and 5 colleagues. He separated each sample into serum and red blood cells. Then he began mixing them, serum from one person with cells from another, and watched what happened. In some combinations, the red blood cells clumped together, agglutinated into visible clusters. In others, they remained evenly dispersed. The pattern was not random. It was systematic, repeatable, predictable. Landsteiner had discovered that human blood fell into distinct groups. He initially identified 3, later a 4th was added, based on the presence or absence of specific antigens on the cell surface. He called them A, B, and C, the last of which was later renamed O. The implications were revolutionary, though the revolution was slow to arrive. Landsteiner published his findings in a brief paper in 1901. It received almost no attention. The medical establishment was not ready. The concept of molecular identity on cell surfaces was too abstract, too far removed from clinical practice. It would take years before hospitals began typing blood before transfusions, and even longer before the practice became routine. Landsteiner himself seemed to understand that he'd only opened a door, not walked through it. He continued working on blood serology for decades, driven by a suspicion that ABO was not the complete picture. Transfusions that should have been compatible, donor and recipient matched for A, B, and O, still sometimes failed. Patients still sometimes died. There was something else on those red blood cells, something ABO typing could not detect. He was right. But the proof would not come for another 36 years, and it would arrive not through human Tundisan blood at all, but through the blood of a small brown monkey strapped to a laboratory table on the other side of the Atlantic. The next chapter in this story was about to be written, not in the elegant clinics of Vienna, but in a cramped research lab in New York, where 2 men were studying immune reactions in primates and stumbled onto a discovery that would change everything we knew about blood, pregnancy, and the invisible war. A mother's body could wage against her own child, but that discovery would raise its own haunting question. If blood carried such dangerous secrets, if the wrong combination could destroy cells and kill patients and murder infants in the womb, then what did it mean that humanity had spent its entire existence transfusing, breeding, mixing blood in total ignorance of those secrets? How many died not from disease or disaster, but from a molecular mismatch no one could see? And how many of those deaths were recorded as God's will, bad luck, or simply the natural cruelty of a world that consumed its young without explanation? The answer to that question was not written in any archive. It was written in blood, and in the silence of all the centuries that refused to read it. Karl Landsteiner never stopped listening to the silence between his own discoveries. Even after the Nobel Prize arrived in 1930, honouring his identification of the ABO blood groups 3 decades earlier, he carried with him a restlessness that no award could quiet. The prize recognised what he had already proven, that human blood was not universal, that it came in types, that matching those types could mean the difference between life and death on the operating table. Hospitals across Europe and America were finally, slowly, adopting routine blood typing before transfusions. The era of lethal guesswork was ending. But Landsteiner knew something the celebration overlooked. The system was incomplete. There were still deaths that ABO could not explain. Patients typed and cross-matched with textbook precision, who nonetheless convulsed on the table, whose blood darkened in the tubes, whose kidneys shut down as though the transfused blood had carried poison instead of life. He documented these cases. He filed them. He returned to them late at night in his laboratory at the Rockefeller Institute in New York, where he had relocated from Vienna years earlier, a quiet Austrian émigré surrounded by younger researchers who admired his precision but did not always share his obsession. The problem was specific and maddening. In a small but consistent percentage of transfusions, everything looked right on paper. Donor and recipient shared the same ABO group. The cross-match showed no visible agglutination. The serum and cells appeared compatible, and yet the patient reacted, sometimes mildly. A fever, a chill, a transient drop in blood pressure, sometimes catastrophically. The reactions followed a pattern that did not map onto ABO at all. Something else was lurking on the surface of those red blood cells, an antigen that the existing classification system could not see. Landsteiner suspected this as early as the 1920s. He and his colleague Philip Levine had identified additional blood group markers, the M, N, and P antigens, through painstaking serological work, proving that the landscape of blood cell surfaces was far more complex than anyone had imagined. But none of these new markers fully explained the mysterious transfusion failures. The ghost remained. What haunted Landsteiner most, though he rarely expressed it in emotional terms, was not the transfusion problem alone. It was the pregnancies. By the early 1930s, scattered reports had begun appearing in obstetric journals, describing a condition that physicians called erythroblastosis fetalis, a devastating disease of the newborn in which the infant's red blood cells were destroyed at an alarming rate, flooding the tiny body with bilirubin, causing jaundice so severe the skin turned golden brown, swelling the liver and spleen, sometimes killing the child within hours of birth. The condition had been observed for decades, described under various names, but no one understood its cause. It seemed to run in families, or rather, it ran in pregnancies. A mother's first child would be healthy, a second might show mild jaundice, her third would be severely affected, her fourth might be stillborn. The pattern was progressive, as though something were building in the mother's body with each successive pregnancy, growing stronger, more lethal, more precise in its destruction. In 1932, a physician named Ruth Darrow proposed a hypothesis that was decades ahead of its time. Darrow herself had lost 3 infants to erythroblastosis fetalis. She was not merely a researcher, she was a witness, a survivor, a mother who had held dying children in her arms and then gone back to her laboratory to ask why. Her theory was elegant and terrible. She suggested that the mother's body was producing antibodies against something in the fetal blood, something the fetus had inherited from its father that the mother's immune system recognized as foreign. Those antibodies, she argued, crossed the placenta and attacked the baby's red blood cells. The disease was not an infection. It was not a toxin. It was an immune response, the mother's body treating her own child as an invader. Darrow was almost entirely correct. She identified the mechanism with remarkable precision. But she was wrong about one critical detail. She believed the target was fetal hemoglobin, the oxygen-carrying protein inside red blood cells, rather than an antigen on their surface. That single error kept the full picture just out of reach. Her paper was published, noted by a few specialists, and then largely forgotten. The obstetric community was not ready to accept that a mother's immune system could be the agent of her child's destruction. It contradicted too many assumptions. about the protective nature of pregnancy, about the placenta as a perfect barrier, about the fundamental compatibility between mother and child. If Darrow was right, then pregnancy itself was a site of potential biological warfare, and no one wanted to believe that. Meanwhile, Landsteiner continued his serological investigations, testing blood samples against novel antibodies, searching for the variable he knew must exist. He was in his 70s by the late 1930s, working with a younger colleague named Alexander Wiener, an immunologist with a sharp mind and a combative temperament, who would later claim more credit for the discovery than some historians believe he deserved. Together, and in parallel with a separate effort by Levine and Rufus Stetson, they were closing in on the invisible antigen. Levine and Stetson actually reached a crucial milestone first. In 1939, they published a case report that should have shaken the medical world. A woman had delivered a stillborn infant, then nearly died when she was transfused with her husband's blood. Blood that was ABO compatible. Her serum contained an antibody that agglutinated not only her husband's cells, but the cells of roughly 80% of random donors. Something in her blood was reacting to something on those cells, something that had nothing to do with A, B, or O. Levine and Stetson had found the ghost, but they did not yet have a name for it, and they did not fully grasp what it meant. That name would come 2 years later from Landsteiner and Wiener's monkey experiments. But by then, Landsteiner himself was running out of time. He would die in 1943 at his laboratory bench, suffering a heart attack while conducting an experiment. He died as he'd lived, searching. The full significance of what he and Wiener had found, the clinical implications for pregnancy, the connection to erythroblastosis fetalis, the scale of the tragedy it could explain and eventually prevent, all of that would unfold in the years after his death. He'd spent 4 decades chasing the secrets hidden on the surface of red blood cells, and in the end he uncovered the most dangerous one. But he never lived to see it applied. He never saw the first infant saved by the knowledge he had generated. He never knew how many had been lost to the silence that preceded it. And perhaps the cruelest irony of all, the discovery was already implicit in the failures he had documented for years. Every unexplained transfusion reaction, every stillborn child delivered to a healthy mother, every case of erythroblastosis fetalis that physicians had recorded with clinical detachment and no understanding. The evidence had been accumulating in hospitals and morgues and parish records for centuries. The answer had been circulating in the blood of millions of people, visible to anyone with the right antibody and the right question. But the right question took the longest to arrive. Not because it was complex, but because it required imagining something that medicine, religion, and culture had all conspired to make unthinkable. That a mother's body could be the instrument of a child's death, and that the weapon was not malice, not sin, not curse, but a protein so small it could not be seen with the most powerful microscope of its age. The protein had been there all along, waiting on the surface of every red blood cell in every Rh-positive human being who had ever lived, silent, patient, invisible, and lethal only under one very specific condition, when it met a body that did not recognize it, a body that would read its presence as a threat, a body that belonged, in most cases, to a mother carrying a child whose blood spoke a language her own blood could not understand. That language was about to be decoded, but the decoding would begin not with a mother or a child. It would begin with a monkey, a small rhesus macaque in a New York laboratory, whose blood would lend its name to one of the most consequential discoveries in the history of medicine, and to one of the most quietly devastating tragedies in the history of human reproduction. The monkey weighed less than 10 pounds. It sat in a metal cage in a laboratory at the Rockefeller Institute, indifferent to the fact that its blood was about to give a name to something that had been killing human infants for millennia. Rhesus macaques were common laboratory animals in the 1930s, cheap, hardy, physiologically similar enough to humans to be useful, different enough to be expendable. Landsteiner and Wiener were not studying pregnancy. They were not thinking about dead babies. They were doing what immunologists do, probing the boundaries of biological identity by forcing one organism's blood to confront another's and watching what happened at the border. The experiment was methodical in its simplicity. They drew blood from the rhesus monkey and injected it into rabbits. The rabbits' immune systems, encountering foreign proteins, did what immune systems are designed to do. They manufactured antibodies, specific, targeted, precise molecular weapons shaped to recognize and neutralize the alien material. Landsteiner and Wiener then took those rabbit antibodies and mixed them with human blood samples. What they expected was straightforward. Since monkey blood and human blood were from different species, the antibodies would react with some human cells and not others, revealing differences in surface chemistry that might correspond to the unexplained transfusion reactions that had plagued clinical medicine for decades. What they found was a clean division. Approximately 85% of the human blood samples agglutinated. The red blood cells clumped together when exposed to the anti-rhesus antibodies, indicating they carried something on their surface that the antibodies recognized. The remaining 15% showed no reaction at all. Their cells remained smooth, dispersed, unmarked. Whatever protein the monkey blood shared with the majority of humans, this minority lacked it entirely. Landsteiner and Wiener called the protein the rhesus factor, Rh factor for short. Those who carried it were Rh positive. Those who did not were Rh negative. The nomenclature was almost casual, a laboratory shorthand derived from the animal that had provided the initial antibodies. Neither man could have known that this abbreviation would become one of the most consequential labels in the history of human medicine, that it would be printed on billions of blood typing cards, whispered in maternity wards, stamped on military dog tags, and eventually encoded into the anxieties of every Rh-negative woman who had ever become pregnant. The paper was published in 1940. It was technically precise and clinically modest, describing a new blood group system without making dramatic claims about its implications. But the implications were already gathering force in other laboratories and other minds. Philip Levine, who had worked with Landsteiner years earlier and had published his own case of unexplained transfusion incompatibility in 1939, immediately recognized the connection. The antibody in the woman who'd nearly died after receiving her husband's blood. The antibody that reacted with 80% of random donors was targeting the same thing, the Rh factor. Levine began testing his hypothesis with a growing sense of urgency. If the Rh factor could cause deadly transfusion reactions between adults, what was it doing during pregnancy? When fetal blood, carrying the father's Rh positive antigen, leaked across the placenta into an Rh negative mother's bloodstream? The answer came in a cascade of clinical observations that transformed abstract serology into concrete tragedy. Levine collected, case after case, Rh negative mothers with Rh positive husbands who had experienced multiple stillbirths, neonatal deaths, or severely jaundiced infants. In each case, the mother's serum contained anti-Rh antibodies, the same antibodies that cause transfusion reactions in adults. Her immune system had been sensitized by her own pregnancies. Each exposure to fetal Rh-positive blood had strengthened the response. The first pregnancy was usually safe because the initial exposure produced only a weak immune reaction, too slow and too small to harm the baby before birth. But the antibodies persisted. They waited. And when the next Rh-positive pregnancy occurred, the immune system was ready. This time the response was swift, aggressive, overwhelming. Antibodies of a type small enough to cross the placental barrier, immunoglobulin G, IgG, flooded into the fetal circulation and began binding to the baby's red blood cells, marking them for destruction. The clinical picture was now horrifyingly clear. Erythroblastosis fetalis, the disease that had been described for decades without understanding. was not a mystery at all. It was Rh incompatibility playing out in the womb. The mother's immune system, primed by a previous pregnancy, was destroying her current baby's red blood cells. The fetal bone marrow, desperate to replace the cells being annihilated, released immature red blood cells, erythroblasts, into the bloodstream, giving the disease its name. The fetal liver and spleen swelled as they tried to take over blood cell production. Bilirubin, the breakdown product of destroyed hemoglobin, accumulated to toxic levels, staining the skin yellow, crossing into the brain, causing a condition called kernicterus, irreversible brain damage marked by deafness, cerebral palsy, and intellectual disability in the children who survived. And many did not survive. The most severe form of the disease, hydrops fetalis, involved massive fluid accumulation throughout the fetal body, swollen abdomen, swollen chest, swollen skin, as the cardiovascular system collapsed under the strain of profound anemia. These babies were often stillborn. Their mothers delivered them knowing already that something was wrong, having felt the movement slow and then stop, having carried the weight of a child whose death was underway before labour even began. The numbers were staggering, though they were never fully counted. Epidemiological estimates suggest that before any form of prevention or treatment existed, Rh hemolytic disease affected approximately 1 in every 200 pregnancies in populations of European descent, the populations with the highest Rh negative frequencies. In absolute terms, this meant tens of thousands of affected infants per year across Europe and North America alone. Some died in utero. Some died within hours of birth. Some survived with brain damage that would shadow their entire lives, and for every severe case there were milder ones. Infants with jaundice that resolved, infants who seemed fine but may have suffered subtle neurological effects that no one in the early 20th century had the tools to detect. The tragedy had a peculiar cruelty built into its structure. It spared first children and punished subsequent ones. It targeted families that wanted more children, families where the mother kept trying, kept hoping, kept believing that the next pregnancy would be different. Each attempt only deepened the danger, as each exposure to Rh-positive fetal blood boosted the mother's antibody levels higher. A woman who had lost 2 babies to Rh disease and tried a third time was almost certainly going to lose that child as well, unless something intervened. Nothing did. Not for years. Not for decades. The discovery of the Rh factor in 1940 explained the disease but did nothing to stop it. Doctors could now tell a woman why her babies were dying. They could draw her blood, test for anti-Rh antibodies, measure the rising titers with each successive pregnancy, and predict with increasing accuracy how severely the next infant would be affected. But they could not prevent the sensitization. They could not remove the antibodies. They could not protect the fetus from its own mother's immune response. Diagnosis without treatment is its own kind of torment, the medical equivalent of being able to name the fire but not possessing water. And so for more than 2 decades after Landsteiner and Wiener's publication, the knowing continued alongside the dying. Hospitals could type blood. They could identify at-risk pregnancies. They could watch the antibody levels climb with each prenatal visit. And then they could stand at the bedside as the infant arrived yellow and swollen and gasping, and they could say with the authority of modern science exactly what was happening and exactly why. What they could not say was how to stop it. That answer was still coming. It would arrive from unexpected directions, from a butterfly researcher in Liverpool, from a prison in New York, from the deliberate wounding of volunteers who agreed to let their own blood be turned into a weapon against a disease they would never personally suffer. But between the naming of the enemy and the forging of the shield, there stretched a long and terrible corridor of years in which mothers and doctors alike stood in the same helpless position humanity had always occupied, watching children die, understanding at last the reason, and possessing nothing with which to change it. What does it feel like when your body becomes the enemy of the life it created? not metaphorically, not in the language of psychology or postpartum grief, but cellularly, molecularly, in the silent chemistry of blood meeting blood across the thin membrane of the placenta. There is no pain the mother can feel, no symptom she can detect. The war happens below the threshold of sensation, in a theatre so small that millions of battles can be fought and lost on the head of a pin. She feels her baby kick. She feels it grow. She may feel nothing unusual at all until the day the kicking stops, or until the delivery reveals an infant whose skin is the colour of old gold and whose breathing sounds like something drowning from the inside. The immunology of Rh disease is precise, in a way that makes it almost elegant, if elegance can be obscene. During a first pregnancy, small numbers of fetal red blood cells cross the placental barrier into the mother's circulation. This is normal. It happens in virtually every pregnancy, Rh compatible or not. The placenta is not a perfect wall. It is a living interface, a dense network of blood vessels where maternal and fetal circulations come close enough to exchange oxygen and nutrients without actually mixing. But cells slip through, especially during the third trimester, when the placenta is under the greatest mechanical stress, especially during labour and delivery, when the physical disruption of birth can release a significant volume of fetal blood into the maternal system. In most cases, this cellular trespass is harmless. The mother's immune system either ignores the foreign cells or mounts a response so weak and so slow that it has no clinical consequence. But if the mother is Rh negative and the fetal cells are Rh positive, that first exposure plants a seed. Her immune system registers the Rh antigen, the D protein on the surface of those foreign red blood cells, as something it has never encountered before. It begins producing antibodies, but slowly. The primary immune response to a novel antigen is measured, cautious, as though the body is unsure whether this stranger is truly a threat. By the time a meaningful number of anti-D antibodies are circulating in the mother's blood, the pregnancy is usually over. The baby has been born, the fetal cells have been cleared, and the crisis that never quite materialized seems to have passed. The first child is almost always safe, but the immune system does not forget. This is the central fact of Rh disease, the biological principle that transformed a minor immunological curiosity into a generational catastrophe. Memory B cells, long-lived immune cells trained during that first exposure, remain in the mother's body indefinitely. They're sentinels, stationed in the bone marrow and lymph nodes, carrying the molecular blueprint for anti-D antibodies. They wait. Months, years, decades if necessary. And when the next Rh-positive pregnancy occurs, when fetal cells again cross the placenta carrying the D antigen, the memory cells activate. This time, there is no hesitation, no slow, tentative primary response. The secondary immune response is fast, massive, and devastating. Anti-D antibodies of the IgG class, small enough to cross the placenta, flood the mother's circulation and begin streaming into the fetal bloodstream. Once there, they do exactly what antibodies are designed to do. They bind to the target. Every fetal red blood cell carrying the D antigen becomes coated with maternal antibodies, tagged for destruction. The fetal spleen, the organ responsible for filtering damaged or marked blood cells, goes into overdrive. It pulls the antibody-coated cells from circulation and destroys them, recycling the iron and hemoglobin, releasing bilirubin as a waste product. Under normal conditions, bilirubin is processed by the liver and excreted harmlessly, but the fetal liver is immature. It cannot keep pace with the volume of bilirubin being generated by the wholesale destruction of its own red blood cells. Bilirubin accumulates. It stains the skin and the whites of the eyes yellow, the jaundice that midwives and physicians had observed for centuries without understanding its cause. And if the levels rise high enough, bilirubin crosses another barrier, one far more fragile than the placenta. It crosses the blood-brain barrier and deposits in the basal ganglia and brainstem, causing kernicterus, a word derived from the German for nuclear jaundice, describing the yellow staining of brain tissue that pathologists observed at autopsy in infants who had died of severe hemolytic disease. The children who survived kernicterus bore its marks for life: hearing loss, movement disorders, cognitive impairment. The damage was irreversible, written into the architecture of the developing brain by a molecule that should never have reached it. And the terrible arithmetic of the disease meant that each subsequent pregnancy carried greater risk than the last. The mother's immune memory grew sharper with each exposure. Her antibody titers climbed higher. The attack on each successive fetus began earlier in gestation and proceeded with greater ferocity. A woman whose second child was mildly jaundiced might deliver a third child with severe anemia. Her fourth might be stillborn at 30 weeks, the tiny body swollen with the fluid accumulation of hydrops fetalis, the end stage of the disease, where the fetal heart, overwhelmed by the effort of circulating an ever-diminishing supply of red blood cells, simply failed. Hydrops fetalis was the horror at the bottom of the well. Physicians who attended these deliveries described infants so swollen they were nearly unrecognizable as human. Abdomen distended with ascitic fluid, chest filled with pleural effusions, skin tight and glistening, the face puffy and discoloured. Many were stillborn. Those born alive rarely survived more than a few hours. The cause of death was usually cardiac failure compounded by profound anemia. The baby's blood had been so thoroughly depleted of functional red blood cells that oxygen delivery to the tissues had effectively ceased. The heart, starved of oxygen itself, beat faster and faster in a futile attempt to compensate, then gave out. And in the delivery room, the mother, alive, physically unharmed. Her body had won the war it was never supposed to fight. Her immune system had performed flawlessly, identifying a foreign antigen, manufacturing targeted antibodies, deploying them across the placental barrier with lethal efficiency. Every step of the process was a textbook example of adaptive immunity functioning exactly as evolution had designed it. The only problem was that the target was not a pathogen, not a parasite, not an invading organism. The target was her child. How does one reconcile that? The physicians of the 1940s and 1950s, who could now explain the mechanism with clinical precision, struggled with the philosophical weight of what they were describing. The language of immunology is military: attack, defense, invasion, destruction. And it mapped onto Rh disease with uncomfortable accuracy. The mother's body treated the fetus as an enemy combatant. The placenta became a contested border. The antibodies were weapons deployed across that border with increasing force in each successive conflict. And the casualty was always the same: the smallest, most vulnerable participant in the war. Some physicians tried to soften the language. They spoke of incompatibility rather than attack. They described the immune response as misdirected rather than hostile. They emphasized that the mother had no awareness of what was happening, no intent, no agency in the destruction of her child. These were important distinctions, clinically and emotionally, but they did not change the outcome. The babies were still dying. The mothers were still delivering stillborn infants and watching newborns fade in the hours after birth. And the disease was still progressing with each pregnancy, punishing the very act of trying again, of hoping that this time might be different. In obstetric wards across the developed world, a grim ritual took shape. Rh-negative women were identified at their first prenatal visit. The husband's blood was typed. If the husband was Rh positive, the pregnancy was flagged as at risk. Antibody screens were performed at regular intervals, tracking the mother's anti-D titers like a rising floodwater mark. Physicians could predict with growing accuracy which pregnancies would be severely affected. They could counsel women about the risks of further pregnancies. They could prepare neonatal teams for difficult deliveries. What they could not do was intervene. They could watch the catastrophe approach with the clarity of modern diagnostic science and the helplessness of medieval midwifery. The disease had been named, mapped, and understood. But understanding without the power to act is a particular kind of cruelty. The cruelty of a witness who sees the fire, knows the cause, and has no water. That water was being sought. In laboratories and clinics on both sides of the Atlantic, researchers were already working on solutions, some brutal, some ingenious, all driven by the urgency of watching preventable deaths continue in real time. The first solution would not prevent the disease at all. It would attempt something far more radical and far more dangerous, reaching into the body of a dying newborn and replacing its blood entirely, one syringe at a time, racing against the clock of bilirubin toxicity with nothing but steady hands and the thin hope that fresh blood could outrun a mother's antibodies. She lost 3 children, 3 pregnancies carried to term or near term, 3 infants delivered into a world that their own blood could not survive. And then she went back to her laboratory and tried to understand why. Ruth Darrow's name does not appear in most popular histories of medicine. It does not adorn the walls of medical schools or feature in the triumphant narratives of 20th century breakthroughs. She was a physician, a pathologist, a researcher working in Chicago in the early 1930s, and she was also a mother who'd been hollowed out by a pattern she recognized clinically long before anyone else dared to name it. Her children had died of erythroblastosis fetalis. She had held them, she'd examined them, and then she'd sat down and written a paper that proposed with devastating logical clarity the mechanism by which a mother's body could destroy her own offspring. The year was 1932. Darrow's hypothesis was published in the Archives of Pathology, a respected but not widely read journal. The paper was careful, methodical, built on a foundation of clinical observation and immunological reasoning that was years ahead of the prevailing wisdom. She argued that the disease was not caused by an infection, not by a toxin passed from mother to child, not by a deficiency in the fetal blood itself. It was caused by antibodies. The mother, Darrow proposed, was exposed to some component of fetal blood during pregnancy or delivery. Her immune system, recognizing that component as foreign, produced antibodies against it. Those antibodies then crossed the placenta in subsequent pregnancies and attacked the fetal red blood cells, causing the hemolysis, the jaundice, the anemia, the organ failure, the death. The logic was almost perfect. Darrow identified the correct mechanism, maternal immunization against a fetal blood component, and the correct pathway, transplacental transfer of antibodies. She explained why first pregnancies were usually spared, and why the disease worsened with each subsequent pregnancy. She even suggested that the offending antigen was inherited from the father, which explained why the mother's immune system did not recognize it. In every essential respect, her hypothesis described our hemolytic disease as it would eventually be understood. But she made one mistake. She believed the target antigen was fetal hemoglobin, the oxygen-carrying molecule inside red blood cells, rather than a protein on their surface. It was a small error, a detail that could easily have been corrected with the right experimental tools. But in 1932, those tools did not yet exist. The Rh factor had not been discovered. The concept of surface antigens on red blood cells was still in its infancy. Darrow was working at the edge of what was knowable, and she reached slightly beyond it. The response to her paper was not hostile. It was worse. It was silence. The medical community acknowledged her work with the polite indifference that academia reserves for ideas that arrive too early. A few specialists noted the hypothesis. Fewer tested it. Most continued treating erythroblastosis fetalis as a clinical puzzle without a clear etiology, managing symptoms when they could, watching infants die when they could not. Darrow's insight that the disease was an immune phenomenon rooted in maternal-fetal blood incompatibility did not fit the conceptual framework of 1930s obstetrics. Pregnancy was understood as a cooperative biological process, not a site of immunological conflict. The placenta was imagined as a protective barrier, not a permeable membrane through which molecular warfare could be conducted, and the idea that a mother's body could produce weapons specifically designed to kill her own child was, for many physicians, simply too disturbing to entertain seriously. 7 years later, in 1939, Philip Levine and Rufus Stetson would publish the case that cracked the door open wider. Their patient was a woman who had delivered a stillborn infant and then suffered a near-fatal transfusion reaction when given her husband's blood. Blood that was ABO-compatible. Levine and Stetson found an antibody in the woman's serum that reacted with her husband's red blood cells and with the cells of approximately 80% of random donors. They did not yet know what antigen this antibody was targeting, but the clinical picture was unmistakable. The woman had been immunized by her own pregnancy, sensitized by fetal blood cells carrying a paternal antigen her body did not recognize. The stillborn infant was the casualty. The transfusion reaction was the proof. Levine pursued the connection with the tenacity of a man who sensed he was holding a thread that could unravel the entire mystery. After Landsteiner and Wiener published their discovery of the Rh factor in 1940, Levine quickly established that the antibody in his 1939 case, and in dozens of similar cases he had been collecting, was directed against the Rh antigen. The picture snapped into focus. Rh-negative mothers exposed to Rh-positive fetal blood produced anti-Rh antibodies. Those antibodies caused erythroblastosis fetalis, the stillbirths, the jaundice, the hydrops, the brain damage. All of it was Rh disease. Darrow's hypothesis had been right in its architecture, wrong only in identifying the specific molecular target. Levine's work supplied the target. The mystery was solved. But solving a mystery and solving a problem are vastly different enterprises. By the early 1940s, the medical profession understood with crystalline clarity what was happening in Rh-incompatible pregnancies. They could explain the immunology, they could predict the outcomes, they could draw a mother's blood at 12 weeks and again at 20 and again at 28, and watch the antibody titers rise like a tide that everyone knew was coming, but no one could hold back. What they could not do, what no one could do, was prevent the sensitization from occurring in the first place or neutralize the antibodies once they had been formed. The disease was understood, the disease continued, and it continued with a particular cruelty that distinguished it from other medical tragedies of the era. Infectious diseases killed indiscriminately. Cancer struck unpredictably, but IH disease followed a script. It told you exactly when it would strike. In the second or third pregnancy, it told you exactly who was at risk. Rh-negative mothers with Rh-positive partners. It told you exactly how it would progress. Antibodies rising, fetal red blood cells falling, bilirubin climbing. It gave physicians every piece of information they needed except the one that mattered: how to stop it. In this gap between knowledge and power, women lived and suffered. Some were told after their second loss to stop having children. Some ignored the advice. Some were never told at all. In many hospitals, particularly in rural areas and developing countries, Rh typing was not routine, and women went through pregnancy after pregnancy without anyone ever testing their blood or explaining why their babies kept dying. The information existed, the tests existed, the understanding existed, but the infrastructure to deliver that understanding to every pregnant woman on Earth did not. And so, the old pattern persisted alongside the new knowledge, two timelines running in parallel, one in which the disease was named and mapped and discussed at medical conferences, and another in which women buried small coffins and wondered what they had done wrong. Ruth Darrow did not live to see the prevention she had implicitly predicted. She did not see ROGAM. She did not see exchange transfusions or intrauterine procedures or the dramatic collapse of Rh disease mortality in the developed world. What she left behind was a paper, a hypothesis, and the ghost of a question that her contemporaries were not ready to answer. Her contribution was eventually recognized by medical historians, but recognition is a thin substitute for the timely attention that might have accelerated the research by years, might have saved thousands of infants who died in the decade between her hypothesis and its confirmation. The silence that greeted her work was not malicious. It was structural, the silence of a system that could not hear what it was not prepared to believe. And in that silence, another voice was about to emerge. Not from a pathologist's lab or an obstetrician's ward, but from the battlefields of global war, where blood was being spilled on an industrial scale and the urgent need to replace it was about to generate knowledge that peacetime medicine had been too complacent to pursue. War has always been medicine's most terrible teacher. The relationship is as old as surgery itself. The first sutures were battlefield improvisations, the first amputations performed not in hospitals, but in tents pitched within earshot of dying men. And in the 20th century, when industrialized killing reached scales that would have been unimaginable to earlier generations, the medical knowledge extracted from that carnage arrived with a speed and depth that peacetime research could never have matched. Not because wartime physicians were smarter, but because war removes the luxury of patience. When soldiers are bleeding out by the thousands, when field hospitals are overwhelmed, and blood supplies are measured in hours rather than days, the questions that academic medicine debates for decades become emergencies that must be answered now. The Second World War transformed blood science, not gently, not through the careful progression of hypothesis and experiment that textbooks celebrate, but through the brutal arithmetic of supply and demand. Millions of soldiers were wounded. Hundreds of thousands needed transfusions. The military medical establishment, which at the war's outset was still using methods barely advanced beyond the First World War, was forced to industrialize the collection, storage, typing, and distribution of human blood on a scale never before attempted. Blood banks, which had existed in rudimentary form since the late 1930s, expanded explosively. The American Red Cross alone collected more than 13 million pints of blood during the war. Typing became mandatory, cross-matching became routine, and the failures, the transfusion reactions that still occurred despite ABO matching, became impossible to ignore. It was in this crucible that the Rh factor moved from laboratory curiosity to clinical urgency. Military physicians, encountering unexplained transfusion reactions in soldiers who had been correctly typed for ABO, began sending samples back to research laboratories demanding answers. The volume of data was unprecedented. Thousands of transfusions performed under field conditions, meticulously documented because military bureaucracy demanded records, even when the shells were falling, generated a statistical picture that peacetime medicine could never have assembled so quickly. The pattern was clear. A subset of transfusion reactions could not be explained by ABO incompatibility alone. Something else was causing hemolysis in recipients whose blood should have been compatible with their donors. And when researchers tested those cases against the newly discovered Rh system, the mystery dissolved. The recipients were Rh negative, the donors were Rh positive. The anti-Rh antibodies were doing in the veins of soldiers exactly what they were doing in the wombs of Rh negative mothers, destroying red blood cells that carried a protein the recipient's immune system could not tolerate. The military response was characteristically direct. Rh typing was added to the standard blood classification protocol. Soldiers' dog tags, which had previously listed only ABO type, began including Rh status. Blood banks were instructed to match Rh as well as ABO whenever possible. The change saved lives immediately and visibly. Transfusion reaction rates dropped, survival rates for wounded soldiers improved, and the RH system was cemented into the foundation of modern blood banking within a few years. What had taken decades to establish in civilian medicine was accomplished in months under the pressure of military necessity. But the war's contribution to the Earth story went deeper than logistics. The sheer volume of blood being collected, typed and cross-matched generated a population-level dataset that revealed patterns invisible to smaller studies. For the first time, researchers could map the distribution of Rh-negative blood across large populations with statistical confidence. The numbers confirmed what smaller studies had suggested but could not prove. Rh-negative blood was overwhelmingly a European phenomenon. Among soldiers of Western European descent, approximately 15 to 17% were Rh-negative. Among soldiers of African descent, the figure dropped to 7 or 8%. Among soldiers of East Asian descent, it fell below 1%. The geographical gradient was real, it was consistent, and it demanded an explanation that pure chance could not provide. These wartime datasets also revealed something else, something that would become critically important for the prevention of Rh disease in the decades to come. Among the Rh-negative soldiers who received Rh-positive transfusions and were later tested, some developed anti-Rh antibodies and some did not. The immune response was not universal. Some individuals seemed resistant to sensitization, tolerating Rh-positive blood without mounting a detectable antibody response. Others were exquisitely sensitive, producing anti-Rh antibodies after a single exposure. The reasons for this variation were not understood, but the observation was noted and filed away. It would prove crucial when researchers later attempted to prevent sensitization in Rh-negative mothers, because understanding why some immune systems responded aggressively and others did not was essential to designing an intervention that worked. The war ended, the soldiers came home, and the knowledge they had generated, paid for in blood, catalogued in military hospitals, refined under conditions that no ethical review board would ever have approved in peacetime, flowed back into civilian medicine. Blood banks adopted military protocols. Hospitals that had never routinely Rh-typed their patients began doing so. Obstetricians, armed with wartime data confirming the link between Rh incompatibility and hemolytic disease, started screening pregnant women as a matter of course. The infrastructure of modern blood medicine, built to save soldiers, was repurposed to save infants. But the infants were still dying. Screening identified at-risk pregnancies. It did not prevent them. Typing told a woman she was Rh-negative. It did not stop her immune system from attacking her Rh-positive baby. The wartime revolution in blood science had given medicine better maps of the problem, sharper tools for diagnosis, and a deeper understanding of the immunology involved. What it had not given was a treatment. And in the late 1940s and early 1950s, as the full scale of Rh disease became apparent, as hospitals began keeping statistics, as neonatal mortality from hemolytic disease was finally counted rather than estimated, the pressure to find a treatment became unbearable. The pressure was measured in bodies, small bodies, in well-equipped urban hospitals with access to the latest diagnostic technology. Physicians could now identify severely affected pregnancies weeks before delivery. They could measure amniotic fluid bilirubin levels through amniocentesis, a technique pioneered in the 1950s that allowed direct assessment of fetal hemolysis. They could plan deliveries, time inductions, prepare neonatal teams, but preparation without intervention was just organized helplessness. The babies arrived jaundiced and anemic, and the only question was how bad the damage would be. Some physicians refused to accept that passivity. In Toronto, in Boston, in London, a handful of researchers and clinicians began exploring the most radical idea anyone had yet proposed for treating Rh disease, not preventing it, not slowing it, but reaching into the body of a newborn infant and physically replacing its blood. Every drop, draining out the damaged, antibody-coated, bilirubin-saturated blood, and replacing it with fresh, Rh-negative blood that the mother's antibodies could not attack. The procedure was called exchange transfusion. It was brutal. It was dangerous. It required threading a catheter into the umbilical vein of a baby who might weigh less than 5 pounds, withdrawing small volumes of blood and replacing them with donor blood in a painstaking cycle that could take hours. A single error, a bubble of air, a clot, a miscalculation of volume, could kill the infant on the table. It was also, for the first time in the history of this disease, something other than watching and waiting. It was an act. A crude, violent, desperate act that said the dying stops here, that this child will not be surrendered to the elegant machinery of immunological destruction without a fight. The first physicians to attempt exchange transfusion were not celebrated. They were criticized for the risk, for the audacity, for the presumption that they could outrun a mother's antibodies with a syringe and a prayer. But the babies who survived their tables, the babies who left the hospital with functioning brains and pink skin and a future that Gates disease had tried to take from them, those babies were the argument that no critic could answer. The era of treatment had begun, but treatment, as the next years would reveal, was only a way station on the road to something far more ambitious. Not rescuing babies after the damage was done, but preventing the damage from ever occurring. That ambition would require an idea so counterintuitive it bordered on paradox, using the very antibodies that killed babies as a shield to protect them. The infant was hours old, perhaps 5 pounds, perhaps less. A catheter no wider than a drinking straw had been threaded into the stump of its umbilical cord, following the umbilical vein inward toward the liver, the inferior vena cava, the failing heart. On one side of the table, a syringe withdrew 20 milliliters of the baby's blood. Dark, thick with bilirubin, heavy with the wreckage of destroyed red blood cells. On the other side, a second syringe pushed 20 milliliters of fresh donor blood into the infant's body. Then another 20 out, another 20 in. The process was repeated dozens of times over the course of 2 to 3 hours, each exchange replacing a fraction of the baby's poisoned blood with clean cells that the mother's antibodies could not touch. The mathematics was simple, but the execution was terrifying. To achieve a meaningful reduction in bilirubin and antibody levels, the physician needed to exchange approximately twice the infant's total blood volume, roughly 300 to 400 milliliters in a full-term newborn. Every cycle carried risk: infection through the catheter, air embolism from a carelessly drawn syringe, cardiac arrhythmia from these sudden shifts in blood volume and electrolyte concentration, hypothermia as the tiny body lost heat through the procedure, and always hovering over every decision, the knowledge that doing nothing meant certain brain damage or death. The technique was developed and refined primarily by 2 physicians working on opposite sides of the Atlantic. In the United States, Dr. Louis Diamond at Boston Children's Hospital became the leading practitioner of exchange transfusion, performing hundreds of procedures throughout the late 1940s and 1950s and training a generation of pediatricians in the method. In England, similar work was being done at hospitals in London and Liverpool, where the high prevalence of Rh-negative blood in the British population meant a correspondingly high burden of hemolytic disease. Diamond was meticulous, systematic, and deeply aware that he was improvising a procedure for which no manual existed. Each case taught him something: the optimal rate of exchange, the importance of warming the donor blood to body temperature before infusing it, the critical window, how many hours after birth the procedure needed to begin before bilirubin levels reached the threshold for brain damage, the signs that indicated the exchange was working, the infant's skin shifting from golden yellow to pink as clean red blood cells began circulating and the bilirubin load dropped. The results were dramatic. Before exchange transfusion, the mortality rate for severe Rh hemolytic disease was catastrophic. Estimates varied, but some studies placed it above 50% for the most severely affected infants, with many survivors suffering permanent neurological damage. After exchange transfusion became widely practiced, mortality dropped sharply. Infants who would have died or been left brain damaged were surviving intact. The procedure was saving lives in real time, one baby at a time, one agonizing exchange at a time. Diamond became a quiet hero in pediatric medicine, though his name never achieved the public recognition of researchers who later developed prevention. He was a craftsman of survival, working at the point where disease met flesh, where theory became trembling hands and small veins and the clock running down on a newborn's brain. But exchange transfusion was not a solution. It was a rescue operation performed after the disaster had already struck. The mother's antibodies had already crossed the placenta. The fetal red blood cells had already been destroyed. The bilirubin had already accumulated. Exchange transfusion could clean up the aftermath, but it could not prevent the attack. It was also limited by access and expertise. The procedure required specialized equipment, trained physicians, and a reliable supply of right negative donor blood, resources that were concentrated in major urban hospitals in wealthy countries. In rural communities, in developing nations, in any setting without a neonatal intensive care unit, exchange transfusion was simply unavailable. The babies in those places continued to die as they always had, unseen by the medical infrastructure that was celebrating its new capability. And even in the best-equipped hospitals, exchange transfusion had limits. The most severely affected infants, those with hydrops fetalis, whose entire bodies were swollen with fluid and whose cardiovascular systems had already begun to fail, were often beyond rescue. The exchange could clear bilirubin from the blood, but it could not reverse organ damage that had been accumulating for weeks in utero. Some infants were so anemic at birth that their hearts gave out during the procedure itself, unable to tolerate the hemodynamic stress of repeated blood withdrawal and infusion. For these babies, exchange transfusion arrived too late. The damage had been done before they ever drew their first breath. This realization drove a shift in thinking that would prove transformative. If the disease could not always be treated after birth, perhaps it could be treated before birth. In the late 1950s, a New Zealand-born physician named Albert William Liley, working in Auckland, pioneered a technique that pushed the boundaries of what medicine considered possible. Liley proposed performing blood transfusions directly into the fetal abdomen while the baby was still in the womb. Using X-ray guidance, he would insert a needle through the mother's abdominal wall, through the wall of the uterus, and into the fetal peritoneal cavity, where the transfused red blood cells would be absorbed into the fetal circulation through the peritoneal membrane. The procedure was almost unimaginably delicate. The fetus was a moving target inside a fluidous-filled space. The needle had to penetrate multiple layers of tissue without damaging the placenta, the umbilical cord, or the fetus itself. The risks included infection, hemorrhage, premature labor, and fetal death from the procedure itself. Liley performed the first successful intrauterine transfusion in 1963. The infant survived. The medical world took notice. Here was a physician reaching inside the womb with a needle, transfusing blood into an unborn child, fighting the disease at its source rather than waiting for the damaged infant to emerge. The technique was refined over the following years. Ultrasound guidance, which became available in the 1970s, replaced X-ray and dramatically improved the accuracy and safety of the procedure. Direct intravascular transfusion, DICU, injecting blood into the fetal umbilical vein rather than the peritoneal cavity, further improved outcomes. By the 1980s, intrauterine transfusion had become a standard intervention for severely affected pregnancies in specialized centers, allowing fetuses with profound anemia to survive to viability and beyond. But both exchange transfusion and intrauterine transfusion shared the same fundamental limitation. They were treatments, not prevention. They addressed the consequences of Rh sensitization after it had already occurred. The mother's immune system had already been triggered. The antibodies had already been formed. The war had already begun. These procedures were battlefield medicine, heroic, life-saving, essential, but they did nothing to stop the battle from starting. Every Rh-negative woman who became sensitized during her first pregnancy was condemned to an escalating series of interventions in every subsequent pregnancy, each more complex and more dangerous than the last. The disease was being managed, not defeated, and for every managed case in a well-equipped hospital, there were dozens of unmanaged cases in communities without access to specialized neonatal care. The question that haunted the researchers who had pioneered these treatments was deceptively simple. What if you could stop the mother's immune system from ever recognizing the Rh antigen in the first place? What if, instead of fighting the antibodies after they formed, you could prevent their formation entirely? It sounded like an immunological fantasy, suppressing a specific immune response without suppressing the entire immune system. But the clue to how it might be done had been hiding in plain sight, in an observation so well known that everyone had overlooked its implications. The observation was this: in some cases, when a person was passively given antibodies against a specific antigen, antibodies manufactured by someone else's immune system, not their own, the recipient's immune system did not bother to mount its own response against that antigen. The borrowed antibodies did the job. The native immune system stood down. It was as if the body, detecting that the threat was already being handled, decided not to waste resources duplicating the effort. Could this principle be applied to Rh disease? Could you give an Rh-negative mother someone else's anti-D antibodies at just the right moment, after the fetal cells had entered her bloodstream but before her immune system had recognized them, and trick her body into believing the threat had already been neutralized? Could borrowed antibodies prevent native antibodies from ever forming? Two groups of researchers, working independently and in ignorance of each other, were about to find out. One was in Liverpool, led by a man who'd spent years studying the genetics of butterfly wing patterns before turning his attention to human blood. The other was in New York, where the path to an answer would lead through one of America's most infamous prisons. The butterfly connection sounds like a fiction, but it is not. Cyril Clarke was a physician and a geneticist at the University of Liverpool, and before he became one of the architects of Rh disease prevention, he spent years breeding swallowtail butterflies in his garden. Not as a hobby, as serious genetic research. Clarke was studying how wing colour patterns were inherited in Papilio butterflies, crossing different subspecies to trace dominant and recessive traits across generations. The work was painstaking and, to anyone outside the narrow world of Lepidopteran genetics, profoundly obscure. But it taught Clarke something that would prove decisive when he turned his attention to human blood. How to think about inherited incompatibilities. How to trace the passage of a single gene through generations. How to predict what would happen when two organisms carrying different genetic instructions were brought together and asked to produce offspring. The pivot came in the late 1950s. Ronald Finn, a younger colleague at Liverpool, had been studying the distribution of fetal red blood cells in the maternal circulation after delivery. Using a technique called the Kleihauer-Betke test, which exploits the fact that fetal hemoglobin is more resistant to acid than adult hemoglobin, Finn could stain a blood smear and literally count the fetal cells that had crossed the placenta into the mother's bloodstream. The results were striking. In most deliveries, at least some fetal cells made the crossing. The volume varied enormously, from a few cells to several milliliters of fetal blood. But the phenomenon was nearly universal. Every Rh-negative mother delivering an Rh-positive baby was being exposed to the antigen that would trigger her immune system. The sensitizing event was not rare or accidental. It was a routine consequence of normal childbirth. Finn made an observation that changed the direction of everything. He noticed that Rh-negative mothers who were also ABO incompatible with their babies, meaning the mother and fetus had different ABO blood types as well as different Rh types, were significantly less likely to become Rh sensitized than mothers who were ABO compatible. The numbers were dramatic. In ABO compatible pregnancies, roughly 16% of Rh negative mothers developed anti-D antibodies after their first Rh positive baby. In ABO incompatible pregnancies, the rate dropped to less than 2%. Something about ABO incompatibility was protecting against Rh sensitization. The explanation was immunological and, once grasped, breathtakingly elegant. When ABO incompatible fetal cells entered the mother's bloodstream, her pre-existing anti-A or anti-B antibodies that everyone naturally carries against the ABO antigens they lack, immediately attacked and destroyed those fetal cells. The cells were cleared from her circulation so quickly that her immune system never had time to notice the Rh antigen on their surface. The ABO antibodies were acting as an inadvertent shield, wiping out the Rh positive cells before they could trigger Rh sensitization. Nature, it turned out, had already demonstrated the principle of prevention. The question was whether science could replicate it deliberately. Clark and Finn saw the implication immediately. If naturally occurring ABO antibodies could prevent Rh sensitization by destroying fetal cells before the maternal immune system recognized the Rh antigen, then perhaps deliberately administered anti-D antibodies could do the same thing. Give an Rh negative mother a dose of anti-D antibodies shortly after delivery, antibodies manufactured by someone else, harvested from another person's blood, and those borrowed antibodies would seek out and destroy any Rh-positive fetal cells in her circulation before her own immune system could respond. Her body would never be sensitized. She would never produce her own anti-D antibodies. Her next pregnancy would be safe. The concept was counterintuitive to the point of seeming paradoxical. Anti-D antibodies were the weapon that killed babies. They were the molecules that crossed the placenta and destroyed fetal red blood cells in hemolytic disease. Now Clark and Finn were proposing to use those same antibodies as a preventive treatment, to inject them into mothers as a form of protection. It was like suggesting that the best way to prevent arson was to hand the arsonist a match under controlled conditions. The logic was sound, but it required a conceptual leap that many in the medical establishment found difficult to make. Meanwhile, across the Atlantic, the same idea was germinating independently. At Columbia University in New York, a trio of researchers, Vincent Frieda, an obstetrician, John Gorman, a pathologist originally from Australia, and William Pollack, a biochemist at Orthopharmaceutical, had arrived at the same conclusion through a different chain of reasoning. Frieda had been treating Rh disease for years and was intimately familiar with the devastation it caused. Gorman, who had trained in Australia where Rh disease was particularly prevalent due to the country's largely European-descended population, brought a colonial urgency to the problem. He had seen too many babies die in hospitals that lack the resources for exchange transfusion. Pollack contributed expertise in immunoglobulin purification, the technical knowledge of how to extract, concentrate, and sterilize antibodies from human blood for therapeutic use. The New York team and the Liverpool team did not initially know about each other. They worked in parallel, driven by the same observation that ABO incompatibility protected against Rh sensitization, and arriving at the same proposed solution. The convergence was not coincidental. The data were available to anyone who cared to look. Finn's observation about ABO protection had been published. The immunological principle of passive antibody suppression of active immunity was well established in other contexts. It was, for example, the basis of anti-tetanus and anti-rabies prophylaxis, where preformed antibodies were given to patients to prevent their own immune systems from being overwhelmed before they could mount a response. The intellectual foundation was solid. What remained was the experimental proof, and proof required testing in humans, not in rabbits, not in monkeys, in human beings whose immune systems would either respond to the anti-D injection as predicted or not. The Liverpool team began cautiously, testing small doses of anti-D in Rh-negative male volunteers who had been deliberately immunized with Rh-positive blood. The results were encouraging but preliminary. The New York team, more aggressive and better funded, looked for a larger pool of test subjects, men who could be injected with Rh-positive blood, monitored for sensitization, and then given anti-D to see if the sensitization could be suppressed or prevented. They found their subjects in a place that raises questions medicine has never fully answered. A place where the boundary between consent and coercion is as thin as the wall of a cell. A place where men with limited options were offered a transaction, their bodies in exchange for something they valued more than biological safety. The New York team turned to Sing Sing, the maximum security prison on the banks of the Hudson River, where inmates had been volunteering for medical experiments since the 1950s, and where the word volunteering carried a weight that no informed consent form could fully measure. The experiments that took place behind those walls would produce one of the most important medical breakthroughs of the 20th century. They would also leave behind a moral shadow that has never fully lifted, a reminder that the history of medicine is not a clean narrative of progress, but a tangled story in which the lives saved and the lives used are sometimes impossible to separate. Sing Sing Correctional Facility sits on the eastern bank of the Hudson River, about 30 miles north of New York City. In the 1960s, it was one of the most notorious prisons in America, a place of concrete and steel where men served sentences ranging from a few years to life, where violence was routine and autonomy was a memory. It was also, during the middle decades of the 20th century, one of the most productive medical research sites in the country. Pharmaceutical companies, university researchers, and government agencies routinely recruited prisoners for clinical trials. The arrangement was straightforward in its economics. Inmates received small payments, improved living conditions, or simply the break from monotony that participation in a study provided. In return, researchers received what they could not easily obtain elsewhere: large numbers of human subjects who were available for extended observation, who could not leave, and whose consent, however formally documented, was shaped by conditions that made genuine voluntariness difficult to assess. The ethical framework governing human experimentation in the 1960s was a different landscape than the one we inhabit today. The Nuremberg Code, established in 1947 in the aftermath of Nazi medical atrocities, had articulated the principle that research subjects must give voluntary consent free from coercion. But the Code's application to prison populations was ambiguous. Were prisoners capable of voluntary consent? They were confined. Their choices were constrained. The incentives offered, money, privileges, the possibility of favourable parole consideration, operated in an environment where every decision was distorted by the absence of freedom. Yet the practice was widespread, accepted, and rarely questioned by the institutions that benefited from it. Hundreds of studies were conducted in American prisons during this period, testing everything from cosmetics to pharmaceuticals to experimental vaccines. The Rh prevention trials were one among many. Vincent Frieda and John Gorman approached the prison with a specific and carefully designed protocol. They needed to demonstrate two things. First, that injecting Rh-positive red blood cells into Rh-negative men would trigger the production of anti-D antibodies, simulating what happened when an Rh-negative mother was exposed to her Rh-positive baby's blood during delivery. Second, that administering anti-D immunoglobulin shortly after the Rh-positive injection would prevent that antibody response from occurring. The men at Sing Sing were the test subjects. They were Ih-negative, a necessary prerequisite, and they were available for the repeated blood draws and monitoring that the study required over weeks and months. The experiments began in the early 1960s. Groups of inmates were injected with carefully measured doses of Rh-positive red blood cells. Some received anti-D immunoglobulin afterward. Others, the controls, did not. Blood samples were drawn at regular intervals and tested for the development of anti-Rh antibodies. The results were clear and consistent. The control subjects who received Rh-positive cells without anti-D protection became sensitized. Their immune systems detected the foreign antigen and began producing anti-D antibodies, exactly as an Rh-negative mother's body would after an incompatible pregnancy. But the subjects who received anti-D immunoglobulin within 72 hours of the Rh-positive injection showed no sensitization. No anti-D antibodies appeared. The borrowed antibodies had done their work, clearing the Rh-positive cells from circulation before the subject's own immune systems could mount a response. The principle worked. The biological mechanism that Clark and Finn had proposed in Liverpool, that Friedeva and Gorman had theorized in New York, had been confirmed in living human beings. Passive administration of anti-D antibodies could prevent active Rh sensitization. The firewall could be built, the mothers could be protected, the babies could be saved. The data from Sing Sing became the foundation of everything that followed. But the data came from prisoners, men who lived in cells, men whose participation, however documented, occurred within a system that made the concept of free choice more theoretical than real. The question of whether those men were volunteers or subjects, whether they chose or were chosen, remains one of the uncomfortable silences in the history of Rh disease prevention. Medical ethicists have debated it for decades. Some argue that the inmates made rational decisions based on the information available to them, that they understood the risks, and that their participation was as voluntary as any other research subjects. Others point out that consent obtained within a coercive institution is inherently compromised, that no matter how carefully the forms are worded, a prisoner's yes does not carry the same weight as a free person's yes. What is not debated is the outcome. The Sing Sing experiments produced evidence that saved millions of lives. The anti-D immunoglobulin that would eventually become Rogam, the injection given to Rh-negative mothers around the world, was validated in its concept and its dosing through experiments conducted on incarcerated men who had no personal stake in the disease being prevented. They would never be pregnant. They would never carry Rh-positive babies. They would never experience the grief of hemolytic disease. They lent their bodies to a problem that belonged to others, to women, to infants, to families they would never meet. Whether they did so freely or under the subtle compulsions of an institution that controlled every aspect of their existence is a question that the saved millions rarely ask. The parallel work in Liverpool had been progressing along similar lines, though with different subjects and different methods. Clark and Finn conducted their initial experiments on Rh-negative male volunteers, not prisoners, but medical professionals and students who agreed to be injected with Rh-positive cells and then treated with anti-D. Their results confirmed the New York findings. The two teams, working independently on opposite sides of the Atlantic, had converged on the same answer. Anti-D immunoglobulin, given within a narrow window after exposure to Rh-positive blood, prevented sensitization with remarkable reliability. The next step was to test it in the population that actually mattered, Rh-negative women who had just delivered Rh-positive babies. The clinical trials began in the mid-1960s. In both the United States and the United Kingdom, Rh-negative mothers were enrolled after delivery and randomized to receive either anti-D immunoglobulin or a placebo. The results were followed over subsequent pregnancies. Did the treated mothers remain unsensitized? Did their next babies escape hemolytic disease? The answer, when it came, was overwhelming. Among untreated mothers, the sensitization rate was approximately 14 to 17% after the first incompatible pregnancy. Among mothers who received anti-D immunoglobulin within 72 hours of delivery, the sensitization rate dropped to less than 1%. The treatment was not merely effective, it was transformative. The implications rippled outward from the study results like waves from a stone dropped into still water. If every Rh-negative mother could be given anti-ID after every delivery of an Rh-positive baby, Rh sensitization could be virtually eliminated. No sensitization meant no anti-D antibodies in subsequent pregnancies. No antibodies meant no hemolytic disease. No hemolytic disease meant no exchange transfusions, no intrauterine procedures, no hydrops fetalis, no connectorus, no small coffins. The entire cascade of suffering that had been playing out for millennia could be interrupted at its very first step, the moment of immunological recognition, the instant when a mother's body first encountered the foreign protein on her baby's blood cells and decided to remember it. But interrupting that moment required something specific and deeply strange. It required anti-D antibodies, large quantities of them, purified and sterilized and packaged for injection. And anti-D antibodies do not grow in laboratories. They do not emerge from chemical synthesis or recombinant DNA technology. They come from one source and one source only: the blood of Rh-negative individuals who have already been sensitized to the Rh antigen, people whose immune systems have already done the thing the treatment is designed to prevent, people who carry, circulating in their veins, the very molecules that once killed babies, now repurposed as the shield that would protect them. Where do you find such people? How do you obtain their blood in sufficient quantities to supply a global prevention program? And what does it mean to build a system of salvation on a foundation of deliberately induced immune responses in human bodies turned into living pharmaceutical factories? The answer to that question would give the world one of its most extraordinary and least known medical heroes. A man from Australia whose arm was punctured more than 1,000 times over 6 decades, whose blood was harvested and processed and injected into millions of women he would never meet, and whose quiet, stubborn generosity became the biological infrastructure of survival for an estimated 2.5 million children. In 1951, a 14-year-old boy in Australia underwent major chest surgery. The operation required massive blood transfusions, 13 units over the course of the procedure and recovery. The boy survived. He was told in the plain language that adults use when they want children to understand the gravity of what has happened, that the blood of strangers had saved his life. The boy's name was James Harrison, and he made a decision in that hospital bed that would take decades to fulfill. When he turned 18, the minimum age for blood donation in Australia, he would begin giving blood. He would repay the debt. Harrison kept his promise. At 18, he walked into a blood donation centre and offered his arm. The routine typing revealed something unexpected. Harrison was Rh-negative, and his blood contained anti-D antibodies, the result almost certainly of the massive Rh-positive transfusions he had received during his childhood surgery. His immune system had been sensitized years earlier, and it had been quietly producing anti-D antibodies ever since. In most contexts, this would have been a clinical footnote. A blood bank would note the antibody, flag the sample, and use it only for Rh-negative recipients. But in the 1960s, as the race to develop Rh disease prevention accelerated, Harrison's blood became something else entirely. It became a resource, a rare, irreplaceable, biologically unique resource. The Australian Red Cross Blood Service recognised what they had. Harrison's anti-D antibodies were precisely the molecules needed to manufacture anti-D immunoglobulin, the injection that could prevent Rh sensitization in pregnant women. Australia was facing a severe burden of Rh disease. The country's largely European-descended population had IAH-negative rates comparable to those in Britain, and hemolytic disease of the newborn was claiming hundreds of Australian babies every year. The development of an Australian anti-D program was a national priority, and it needed donors, Rh-negative individuals with high titers of anti-D antibodies who were willing to donate plasma regularly and indefinitely. Harrison was willing, more than willing. Over the next 60 years, James Harrison donated blood approximately every 2 to 3 weeks. His donations were not standard whole blood donations, which take about 10 minutes. They were plasmapheresis donations, a longer process in which blood is drawn, the plasma separated and collected, and the remaining blood components returned to the donor's body. Each session took about an hour. Harrison did this more than 1,100 times between 1954 and 2018, when he was forced to retire at age 81 under Australian donor age limits. His plasma, rich in anti-D antibodies, was processed by the Commonwealth Serum Laboratories and used to manufacture a product called anti-D immunoglobulin, the Australian equivalent of the American Rogam. That product was injected into Rh-negative mothers across Australia for more than half a century. The numbers are almost incomprehensible in their scale. The Australian Red Cross estimates that Harrison's donations contributed to anti-D injections given to more than 3 million women. Those injections prevented Rh sensitization in the vast majority of cases. The downstream effect, the babies who were born healthy because their mothers never developed the antibodies that would have attacked them, is estimated at approximately 2.5 million. 2.5 million children who exist, who grew up, who have children and grandchildren of their own, because one man with an unusual immune response kept showing up at a blood centre every few weeks for 6 decades. Harrison was not the only anti-D donor. Programs in Australia, the United States, the United Kingdom and other countries recruited and maintained panels of Rh-negative donors who had been naturally or deliberately sensitized to produce anti-D antibodies. But the deliberate sensitization is where the story acquires its uncomfortable edge. Not all anti-D donors develop their antibodies naturally, as Harrison had through childhood transfusions. Some were deliberately injected with Rh-positive red blood cells, a process that intentionally triggered the immune response that the anti-D product was designed to prevent in others. These donors were, in immunological terms, deliberately wounded. Their immune systems were provoked into producing a response that would normally be considered pathological, the same response that, in a pregnant woman, would kill her baby. But in a non-pregnant donor, that response was harmless to anyone but the donor himself. The antibodies circulated in his blood, were harvested through plasmapheresis, and were purified into a product that would protect millions. The ethics of this practice have been debated but rarely publicised. The donors were volunteers, yes, they were informed of the risks, which were real but relatively modest. The deliberate sensitization carried a small chance of adverse immune reactions, and the repeated plasmapheresis sessions imposed a cumulative physical burden. But the arrangement had a quality that sat uneasily beside the language of voluntary altruism. These men were being turned into biological factories. Their bodies were production facilities for a pharmaceutical product that generated significant revenue for the companies that processed and sold it. The donors were paid in some programs, though the payments were modest, far below what the product was worth commercially. In other programs, they donated without payment, motivated by the same impulse that drove Harrison, the knowledge that their blood was saving lives. The pharmaceutical dimension cannot be ignored. Anti-D immunoglobulin was and remains a blood-derived product that cannot be synthesized artificially. Every dose requires human plasma from sensitized donors. The supply is perpetually limited. In countries with robust donation programs, supply generally meets demand, though shortages occur. In countries without such programs, anti-D may be unavailable, prohibitively expensive or rationed. The global supply chain for D as a monument to the strange economics of blood products, a market in which the raw material comes from human bodies, where the manufacturing process is biological rather than chemical, and where the end product saves lives that would otherwise be lost to a disease that is entirely preventable. By the time RhoGAM received approval from the US Food and Drug Administration in 1968, the clinical evidence was overwhelming. Large-scale trials in both the United States and the United Kingdom had demonstrated that anti-D immunoglobulin administered to Rh-negative mothers within 72 hours of delivering an Rh-positive baby reduced the rate of Rh sensitization from approximately 16% to less than 1%. Subsequent refinements extended the protection further. A second injection at 28 weeks of gestation during the pregnancy itself caught cases where fetal-maternal hemorrhage occurred before delivery. The combined protocol, prenatal and postnatal anti-D, brought the sensitization rate down to fractions of a percent. The effect on Rh disease mortality was immediate and dramatic. In countries that implemented universal anti-D prophylaxis, the incidence of hemolytic disease of the newborn plummeted. Exchange transfusions, which had been routine in major hospitals, became rare. Intrauterine transfusions, reserved for the most severe cases, became rarer still. Hydrops fetalis, the devastating end stage of Rh disease, went from a regular occurrence to a medical curiosity. Within a single generation, a disease that had killed or damaged tens of thousands of infants every year in the developed world was reduced to a manageable rarity. The reduction was not elimination. Even with anti-D prophylaxis, a small number of women become sensitized. Through failures of the protocol, inadequate dosing, unusually large fetal-maternal hemorrhages, or sensitizing events during pregnancy that occur before the 28-week injection. And in parts of the world where anti-ID is not universally available, the old pattern continues. Rh disease has not been eradicated, it has been displaced, pushed from the centres of medical privilege to the margins, from the countries that can afford prevention to the countries that cannot. But for the women who receive the injection, the millions of Rh-negative mothers who roll up their sleeves at 28 weeks and again after delivery, the shot is invisible. It is a routine part of prenatal care, as unremarkable as a blood pressure check or a urine test. Most of them do not know what it prevents. Most of them do not know about the centuries of dead babies that preceded it. Most of them do not know about Ruth Darrow's grief or Louis Diamond's steady hands or the prisoners at Sing Sing whose bodies provided the proof of concept. And most of them do not know about James Harrison, the man who was saved by blood as a child and spent his life returning the favour, one arm, one needle, 1,100 times. The injection takes less than a minute. The antibodies it contains were harvested from a human being. The protection it provides was built on a foundation of tragedy, ingenuity, ethical compromise, and a kind of generosity so sustained and so quiet that it barely registers as heroism. The blood remembers. The mothers mercifully do not have to. But the story does not end with the invention of a vaccine that is not quite a vaccine, a prevention that works only in the countries wealthy enough to afford it. Because beyond the reach of RhoGAM, beyond the clean corridors of Western prenatal clinics, the old silence continues, and the children it consumes are no less real for being uncounted. There is a map that no one publishes but everyone in global health understands. It is a map of absence, of treatments that exist but do not arrive, of knowledge that is available but not applied, of children who die from conditions that were solved decades ago in other parts of the world. Rh disease sits on that map like a quiet stain, barely visible beneath the larger catastrophes of malaria and tuberculosis and maternal hemorrhage that dominate the headlines and the funding appeals. But it is there, and the children it takes are just as dead as the ones killed by diseases that attract more attention. The arithmetic is stark. Anti-D immunoglobulin has been available since 1968. In the 58 years since its introduction, It has prevented Rh sensitization in tens of millions of pregnancies across the developed world. The incidence of hemolytic disease of the newborn in countries with universal anti-D programs has dropped by more than 95% in the United States, in the United Kingdom, in Australia, in most of Western Europe and Japan. Rh disease is a solved problem, not eliminated entirely but reduced to a level where it is a clinical rarity rather than a routine tragedy. A young obstetrician in London or New York might complete her entire training without ever seeing a case of severe hemolytic disease. The disease has been pushed so far to the margins of clinical experience that many physicians regard it as a historical curiosity, a problem that belongs to the past. But the past is not evenly distributed. In sub-Saharan Africa, where Rh-negative blood occurs at rates of 4 to 8% in some populations, anti-D prophylaxis is sporadically available at best. In many countries, Nigeria, the Democratic Republic of Congo, Ethiopia, Tanzania, the infrastructure for routine Rh typing of pregnant women does not exist in rural areas. Women give birth without ever knowing their blood type. Their babies die of hemolytic disease without ever being diagnosed. The deaths are recorded, if they're recorded at all, as neonatal jaundice or stillbirth or simply as infant mortality. The same formless category that absorbed these deaths for centuries before anyone understood their cause. The World Health Organization has identified Rh disease as a preventable cause of neonatal mortality in low-resource settings, but identification and prevention are separated by a gulf of funding, logistics, and political will. Anti-D immunoglobulin is a blood-derived product. It requires a cold chain, continuous refrigeration from manufacture to injection. It requires trained personnel to administer it at the correct time. It requires, before any of that, a blood typing infrastructure that can identify Rh-negative women during their first pregnancy, before sensitization occurs. Each of these requirements is a barrier. Each barrier is a sentence passed on children who will never know that the treatment that could have saved them has been sitting on a shelf in a European pharmacy for half a century. The economics compound the injustice. Anti-D immunoglobulin is expensive to produce because it comes from human donors. Every vial represents the processed plasma of an Rh-negative individual whose immune system has been deliberately or accidentally sensitized to produce anti-D antibodies. The supply is finite, dependent on donor recruitment and retention, and concentrated in wealthy countries where donation programs are well established. The cost per dose varies widely, but can range from $20 to $300 depending on the country and the source. In nations where the per capita health expenditure is measured in tens of dollars per year, $300 for a single injection is an impossibility. Some efforts have been made to close the gap. International organizations have funded pilot programs to introduce Rh screening and anti-D prophylaxis in selected regions of Africa and South Asia. These programs have demonstrated what everyone already knew, that when Rh-negative women are identified and treated, their babies survive. The programs work. They save lives, and then, when the funding cycle ends, they often collapse. The cold chains break down, the supply of anti-D runs out, the trained staff move to better paying positions, the screening stops, and the dying resumes, invisible and uncounted, in communities that briefly glimpsed prevention and then lost it. There is another dimension to this inequality that is rarely discussed but impossible to ignore. The very blood that produces anti-D immunoglobulin comes overwhelmingly from donors in wealthy nations: the United States, Australia, the United Kingdom, Germany. These countries have the donor programs, the plasmapheresis infrastructure, and the pharmaceutical processing capacity to turn human plasma into a usable medical product. The product is then sold on a global market, but the market follows the money. Anti-D flows to countries that can pay for it. Countries that cannot pay receive charity supplies if they receive anything at all. The biological raw material, human antibodies, is donated for free by individuals like James Harrison. The finished product is sold for profit. The gap between the donated blood and the purchased vial is filled by a pharmaceutical industry that operates, as all industries do, according to the logic of return on investment. This is not a conspiracy. It is a system that functions exactly as designed, producing remarkable outcomes for the populations it was built to serve and negligible outcomes for everyone else. The mothers in Lagos and Dhaka and Addis Ababa are not the system's customers. They are its externalities, the uncounted costs that do not appear on any balance sheet because no one with purchasing power is counting them. And the silence around this disparity is its own kind of erasure. When medical textbooks describe the triumph of anti-D prophylaxis, they rarely mention the populations for whom the triumph has not arrived. When public health reports celebrate the near elimination of Rh disease in the developed world, they do not always include the footnote that the disease continues to kill in the developing world at rates comparable to the pre-Rogam era. The narrative of progress, the story that begins with mysterious infant deaths and ends with a simple injection is a true story. But it is an incomplete story. It describes the experience of the fortunate and calls it universal. The children who die of Rh disease in 2026 do not die because science failed. They die because distribution failed. They die because the economic and logistical systems that deliver medical innovation to wealthy populations do not extend to poor ones with the same urgency or the same reliability. They die in the gap between what is known and what is done. The same gap that has defined the Rh story from the beginning, from the centuries when the disease was invisible to the decades when it was visible but untreatable to the current era, when it is treatable but not universally treated. There are efforts underway to change this. Researchers are working on recombinant antibodies, a synthetic version of the antibody that could be produced in bioreactors rather than harvested from human donors, potentially reducing costs and increasing supply. Monoclonal antibody technology, which has revolutionized cancer treatment and autoimmune therapy, could theoretically be applied to Rh disease prevention. If a recombinant anti-D product could be manufactured at scale, the dependency on human donors would end. The supply would become theoretically unlimited. The cost could drop to a level that makes universal prophylaxis economically feasible even in the poorest countries. But recombinant anti-D has been in development for decades. Progress has been slow. The technical challenges are significant. The anti-D response involves multiple antibody types targeting different epitopes on the Rh protein, and replicating this complexity in a single recombinant product has proven difficult. Several candidates have entered clinical trials. None has yet reached the market. The timeline for a commercially available recombinant anti-D remains uncertain, and while the research continues, the human-derived product remains the only option, and the human donors remain the only source. James Harrison retired in 2018. He was 81 years old. His arm, punctured more than 1,100 times over 63 years, had given enough plasma to protect an estimated 2.5 million children. Australia honoured him. The media called him the man with the golden arm. He accepted the attention with the quiet modesty of someone who did not consider what he'd done to be extraordinary. Just necessary. But when he stopped donating, the Australian anti-D program lost one of its most prolific sources. New donors were recruited, the program continued. But the fragility of a medical system that depends on individual human generosity was briefly, uncomfortably visible. Somewhere tonight, in a clinic with reliable electricity and trained staff and a refrigerator stocked with anti-D immunoglobulin, an Rh-negative woman is receiving an injection that will protect her next child. And somewhere else tonight, in a place without those things, another Rh-negative woman is carrying a pregnancy that no one has screened, that no one will treat, that will end in a way that was preventable 40 years before she was born. The distance between these two women is not measured in miles, it is measured in systems, in the presence or absence of infrastructure that turns knowledge into action, that transforms a solved problem into a lived solution. The blood that kills its own has not stopped killing. It has merely been redirected, channeled away from the populations that can afford to prevent it, and left to flow unchecked through the populations that cannot. The silence around those deaths is not the silence of ignorance. It is the silence of indifference, the quiet consensus that some tragedies matter more than others, that some children are worth saving and others are simply statistics in a report that no one will read. But even in the countries where Rh disease has been conquered, where the injections are routine and the dying has stopped, there remains a question that no injection can answer, a question that preceded the disease and will outlast its prevention, a question that sits at the heart of the RAH mystery and refuses to be resolved by clinical trials or pharmaceutical products or the generous arms of donors who give their blood so that others might live. The question is not how to prevent IH disease. That has been answered. The question is why Rh-negative blood exists at all. Strip away the tragedy, strip away the dead children and the grieving mothers and the prison experiments and the golden-armed donor. Set aside the pharmaceutical economics and the global health disparities and the clinical protocols. Reduce the entire Rh story to its barest biological skeleton, and you are left with a question so fundamental it borders on philosophical. Why does a trait that kills offspring persist in a species whose entire evolutionary purpose is to produce surviving offspring? Natural selection is, at its core, a system of reproductive accounting. Traits that help organisms reproduce spread through populations. Traits that hinder reproduction diminish. Over thousands of generations, the ledger is ruthlessly balanced. A gene that reduces the number of surviving children by even a small percentage should, given sufficient time, be driven to extinction or near extinction in any population subject to normal selective pressures. This is not theory. This is the observed mechanism by which evolution shapes every living species on Earth. And Rh-negative blood, by any standard accounting, is a trait that reduces reproductive success. An Rh-negative mother carrying an Rh-positive baby faces a measurable probability of losing that child to hemolytic disease, a probability that increases with each successive incompatible pregnancy. Before modern medicine, this meant that Rh-negative women in mixed Rh partnerships produced fewer surviving children than Rh-positive women. The selective disadvantage was real, quantifiable, and persistent across the entire history of the human species prior to the 20th century. Yet Rh-negative blood did not disappear. It did not even decline to trace levels. In European populations, it stabilized at approximately 15%, a frequency far too high to be maintained by mutation alone. In the Basque population, it reached 30 to 35%, a concentration so extreme that population geneticists have struggled for decades to explain it within standard evolutionary models. Something kept Rh-negative blood alive. Something counterbalanced the reproductive cost. Something made this apparently disadvantageous trait not merely survivable, but, in certain populations, remarkably common. The simplest explanation is genetic drift, the random fluctuation of gene frequencies in small populations. If a small group of early humans happened to carry a high frequency of the Rh-negative allele, and if that group remained isolated long enough, the frequency could persist or even increase through chance alone, without any selective advantage. This is the founder effect, and it is a well-documented mechanism in population genetics. The Basque population, with its geographic isolation in the Pyrenean Mountains and its cultural resistance to outside marriage, is a textbook candidate for founder effects. A small founding group with unusually high Rh-negative frequency, maintained through millennia of endogamy, could theoretically explain the 35% rate observed today. But the founder effect explanation has weaknesses. It works well for small, truly isolated populations, but it struggles to account for the broader European pattern. Rh-negative blood is not confined to the Basques. It is found at significant frequencies across Western Europe, 15 to 17% in France, Britain, Germany, and Scandinavia. These are not small, isolated populations. They are large, historically mobile, and extensively intermixed through migration, conquest, and trade. For negative blood to maintain 15% frequency across such large and diverse populations requires either extraordinarily persistent founder effects replicated across multiple independent groups, or some form of balancing selection, a hidden advantage that counteracts the reproductive cost. Balancing selection is the idea that a gene can be maintained at intermediate frequency in a population because it provides a benefit that outweighs its cost, particularly when the cost applies only under specific conditions. The classic example is sickle cell disease. The sickle cell allele, when inherited from both parents, causes devastating illness. But when inherited from only one parent, the heterozygous state, it provides significant protection against malaria. In malaria-endemic regions, the survival advantage of carriers outweighs the cost to homozygotes, and the allele is maintained at high frequency. Could a similar mechanism be operating for Rh-negative blood? The hypothesis has been explored, but the evidence remains elusive. Researchers have looked for associations between Rh-negative status and resistance to specific diseases: malaria, plague, tuberculosis, toxoplasmosis. Some studies have found weak correlations. Rh-negative individuals may have slightly different susceptibility to certain parasitic infections, including toxoplasmosis, the common parasite carried by cats that infects a significant percentage of the global population. One study published in the early 2000s suggested that Rh-negative individuals who are infected with toxoplasmosis show different reaction times and personality profiles compared to Rh-positive individuals with the same infection, raising the possibility that Rh status modulates the neurological effects of the parasite. But these findings are preliminary, inconsistent across studies, and far from establishing the kind of clear survival advantage that would explain the persistence of a reproductively costly trait. Other researchers have proposed that the advantage might not be disease resistance, but something else entirely: a physiological or developmental difference that improved survival in specific ancestral environments. Higher altitude tolerance, better cold adaptation, more efficient oxygen transport, enhanced immune surveillance against certain cancers. The theories are creative but speculative, supported by fragments of data rather than robust evidence. No single proposed advantage has gained wide acceptance, and many population geneticists have concluded that the persistence of Rh-negative blood may be explained by a combination of factors rather than any single mechanism: drift in some populations, mild selection in others, cultural practices like endogamy amplifying both. There is another possibility, one that sits at the uncomfortable intersection of genetics and culture. What if Rh-negative blood persisted not because of a hidden biological advantage, but because of a hidden cultural one? What if certain societies, for reasons that may have been religious, political, or simply traditional, preferentially selected for Rh-negative individuals in their leadership structures or reproductive arrangements? This is not as far-fetched as it might sound. We've already seen that European royal families showed elevated rates of Rh-negative blood, rates that cannot be explained by random chance given the size and diversity of the European aristocratic gene pool. If aristocratic families systematically married within bloodlines that happen to carry high Rh-negative frequencies, and if those families also had higher reproductive success due to their wealth and social status, more surviving children, better nutrition, lower infant mortality from non-Rh causes, then the Rh-negative allele could have been amplified through cultural selection operating alongside or even against natural selection. This would make Rh-negative blood not just a genetic variant, but a culturally maintained one. A trait that survived not because evolution favoured it, but because human societies favoured it, for reasons that may have been lost to history. The blue blood of European aristocracy, the divine right of kings, the obsessive genealogical tracking practiced by royal houses for centuries, all of these cultural phenomena could have functioned inadvertently or deliberately as mechanisms for maintaining Rh-negative frequency in elite populations. And from those elite populations, the allele would have diffused into the general population through the inevitable mixing that occurs over centuries of coexistence. This is speculation. It is informed speculation, grounded in documented cultural practices and consistent with the genetic data, but it remains unproven. The truth is that we do not know why Rh-negative blood persists at the frequencies observed in European populations. We have hypotheses, we have fragments of evidence, we have models that can explain parts of the pattern but not the whole. The complete picture remains out of reach, not because the tools to investigate it do not exist, but because the question has never been prioritized by the institutions that fund and direct genetic research. And perhaps that is the deepest irony of the Rh story, a trait that killed tens of thousands of babies every year before modern medicine, a trait that required decades of research and billions of dollars in pharmaceutical infrastructure to manage, a trait that remains a significant cause of neonatal mortality in the developing world. And we still do not fully understand where it came from or why it is here. The medical problem has been solved, at least in principle. The evolutionary riddle has not. The disease has been tamed, but the mystery that created the disease remains wild. Some mysteries endure not because they are unsolvable, but because they're unfunded. Some questions persist not because they lack answers, but because they lack investigators. And some silences, the silence around the origin of Rh-negative blood, the silence around why evolution permits a trait that seems designed to fail, are not the silences of conspiracy or suppression. They are the silences of a world that has moved on, that has filed the question undersolved because the baby stopped dying, even though the deeper puzzle was never touched. But the puzzle is still there, written in the genome of every Rh-negative human being on Earth, encoded in a deletion on chromosome 1 that erased a protein 160 million years old, preserved through mechanisms we cannot identify in populations whose history we do not fully understand, for reasons that may be biological, cultural, accidental, or something else entirely. And somewhere in that puzzle, in the gap between what the gene does and why it survives, there may be a piece of the human story that we have not yet learned to read. The protein that Rh-negative people lack has been around longer than flowering plants, longer than birds, longer than the supercontinent that broke apart to form the Atlantic Ocean. Molecular clock analyses place the origin of the Rh protein complex, the family of transmembrane proteins that includes the D antigen, somewhere in the early Mesozoic more than 160 million years ago. This means the protein was already embedded in mammalian biology when dinosaurs dominated the Earth. It survived the mass extinction that ended the Cretaceous. It crossed into the primate lineage and stayed there, unchanged in its essentials, through the entire evolutionary arc from tiny nocturnal insectivores to great apes. Every primate species tested, chimpanzees, gorillas, orangutans, gibbons, baboons, rhesus macaques, carries the Rh protein on its red blood cells. Every single one. There are no Rh-negative chimpanzees. There are no Rh-negative gorillas. In the entire order of primates, spanning hundreds of species and tens of millions of years of divergent evolution, only one species shows this variation. Humans. That fact alone should give pause. When a protein is conserved, maintained essentially unchanged, across 160 million years of evolutionary time, it typically means the protein is doing something important. Evolution does not preserve useless molecules. The metabolic cost of producing a protein, however small, creates selective pressure against its maintenance, unless it provides a compensating benefit. Proteins that lose their function tend to accumulate mutations and eventually disappear from the genome entirely, degraded into pseudogenes, genetic fossils that retain the structure of a gene but no longer produce a functional product. The Rh protein did not become a pseudogene. It was actively maintained, jealously conserved, passed from species to species across an evolutionary span so vast that it dwarfs the entire history of the human lineage. And then, in one species, our species, it was deleted. Not degraded gradually, not mutated into dysfunction over millions of years, deleted. The most common mechanism for Rh-negative blood in European populations is a complete deletion of the Rhd gene. The gene that encodes the D antigen. The gene is simply absent. The chromosomal region where it should sit contains a gap, flanked by the remnants of the recombination event that removed it. Genetic dating of this deletion event places it somewhere between 25,000 and 40,000 years ago, deep in the last ice age, during a period when modern humans were colonizing Europe, encountering Neanderthals, developing sophisticated tool technologies, and painting the walls of caves with images that still arrest the imagination. The timing is suggestive but ambiguous. 25 to 40,000 years ago was a period of intense evolutionary pressure on human populations in Europe. The climate was brutal. Glacial conditions that drove populations into refugia, small pockets of habitable land surrounded by ice and tundra. Population sizes contracted dramatically. Small groups of humans survived in isolation for generations, subject to exactly the kind of genetic drift and founder effects that can amplify rare variants to high frequency. If the Rhd deletion occurred in one individual within one of these refugial populations, and if that population remained small and isolated for long enough, the deletion could have drifted to significant frequency through pure chance before the glaciers retreated and populations expanded again. This is the standard model, and it is plausible, but it leaves questions unanswered. Why this gene? Of the approximately 20,000 protein-coding genes in the human genome, why did the Rhd gene, a gene conserved for 160 million years, shared by every primate on Earth, become the target of a deletion event that would reach 15% frequency in a major human population? Genetic drift is random. It can amplify any variant, but the persistence of Rh-negative blood at high frequency despite its reproductive cost suggests that something more than drift may be involved. Either the deletion was amplified by chance in an isolated population and then locked in through cultural practices like endogamy, or it provided some benefit we have not identified, a benefit subtle enough to escape detection in modern studies but significant enough to counterbalance the loss of pregnancies over hundreds of generations. There is a third possibility that has received less attention but may be the most intriguing. The Rhd deletion might be linked, physically on a chromosome, to another genetic variant that does provide a clear advantage. This phenomenon, called genetic hitchhiking, occurs when a beneficial mutation arises on the same stretch of DNA as a neutral or even slightly harmful variant. Natural selection favours the beneficial mutation, and the hitchhiking variant is carried along for the ride, increasing in frequency not because it is useful, but because it is physically attached to something that is. If the Rhd deletion sits near a gene that provided a significant survival advantage in Ice Age Europe, a gene involved in cold tolerance, fat metabolism, immune defense, or some other critical function, then the deletion could have been swept to high frequency as a passive passenger rather than a selected trait. This hypothesis is testable, at least in principle. Modern genomic techniques can scan the chromosomal region around the Rhd gene for signatures of positive selection. Patterns in the DNA that indicate a nearby variant was favoured by natural selection. Some preliminary studies have found suggestive signals, but the results are inconsistent and the region is genomically complex, making definitive conclusions difficult. The Rh gene cluster on chromosome 1 is dense with regulatory elements, duplicated sequences and structural variants that complicate analysis. It is, in the language of geneticists, a messy neighbourhood, the kind of genomic region where clear signals are hard to extract from the noise. And then there is the Neanderthal question. Modern Europeans carry approximately 1 to 4% Neanderthal DNA, the legacy of interbreeding events that occurred when Homo sapiens encountered Neanderthals in Europe and the Middle East between 40,000 and 60,000 years ago. Some of that Neanderthal DNA has proven functionally significant. Genes affecting immune response, skin pigmentation, and fat metabolism have been identified as Neanderthal contributions to the modern European genome. Could the RHD deletion have a Neanderthal connection? Could it have been introduced or amplified through admixture with a population that had already lost the D antigen through its own independent evolutionary trajectory? The evidence is thin but not non-existent. In 2021, researchers analysing ancient DNA from Neanderthal specimens identified blood group variants in several individuals, including at least one who appeared to carry a non-functional version of the RHD gene. The sample size was tiny. Ancient DNA work is limited by the availability of well-preserved specimens, and the findings were preliminary. But they opened a door to a provocative possibility that negative blood might not be a purely Homo sapiens innovation. It might be a shared heritage, a variant that appeared independently in both human lineages, or that was exchanged between them during the brief period of coexistence and interbreeding in Ice Age Europe. If that were true, it would add a layer of complexity to the Rh story that challenges the simple narrative of a single mutation spreading through a single population. It would suggest that the absence of the D antigen, far from being a unique modern human quirk, might be a recurrent evolutionary event, a deletion that has happened multiple times in multiple lineages, perhaps because the chromosomal region is inherently unstable, prone to the kind of recombination errors that remove genes entirely, or perhaps because the protein itself, despite its ancient conservation, is not as essential as its evolutionary longevity would suggest, at least not in the environments that human and Neanderthal populations inhabited during the late Pleistocene. None of these hypotheses has been confirmed. None has been ruled out. The origin of Rh-negative blood remains, after nearly a century of research, an open question. Not a mystery in the conspiratorial sense. No one is hiding the answer. The answer simply does not yet exist. The data are insufficient. The studies are too small. The ancient DNA samples are too few. The genomic region is too complex. And the funding, as always, follows the urgency of the moment rather than the curiosity of the question. What we're left with is a gap in the evolutionary record where a protein 160 million years old was erased from a subset of the human genome during a period of extreme environmental stress in a region of the world where isolated populations were being forged by ice and hardship into the ancestors of modern Europeans. That gap has been partially filled by medical science. We know what the deletion does, we know how to manage its consequences, we know how to prevent the deaths it once caused, but the gap in understanding, why it happened, why it persisted, what it means for the broader story of human evolution, remains open. And open questions, in the silence left by incomplete science, become invitations. Invitations to speculation, to mythology, to the construction of narratives that fill the void with meaning even when evidence is absent. The myths that have grown around Rh-negative blood, the alien theories, the Nephilim connections, the secret bloodline conspiracies, are not born from ignorance alone. They're born from the failure of science to provide a complete and satisfying answer to a question that people feel in their bodies, in their pregnancies, in the quiet strangeness of carrying a blood type that sets them apart from 85% of humanity. The science will catch up. It always does, eventually. But in the meantime, the question persists. Not in laboratories or journals, but in the lived experience of millions of people who carry this ancient deletion in their DNA, and wonder, as humans have always wondered, what it means to be different. There is a woman alive tonight who does not know any of this. She does not know about Karl Landsteiner's quiet obsession or Ruth Darrow's buried grief. She has never heard of Philip Levine or the rhesus macaque whose blood lent its name to the invisible line running through her veins. She does not know about the prisoners at Sing Sing who offered their arms so that a theory could be tested, or the man in Australia who gave his blood more than 1,000 times so that children he would never meet could survive their first week of life. She does not know about the Basque Mountains or the Habsburg Jaw, or the parish records of 17th century villages where the same family name appears beside too many small headstones. She knows only what the nurse told her at her first prenatal appointment, reading from a chart with the practiced casualness of someone delivering information that has long since stopped feeling remarkable. RH negative. We will give you a shot at 28 weeks and another after delivery. Nothing to worry about. Nothing to worry about. 4 words that compress centuries of catastrophe into a clinical footnote. 4 words that erase the nameless mothers who buried child after child without understanding why. 4 words that render invisible the decades of research, the ethical compromises, the chance discoveries, the parallel races on opposite sides of the Atlantic, the blood drawn from volunteers and prisoners and one stubborn Australian who believed that what had been given to him ought to be given back. Nothing to worry about, because the worrying has already been done, by people whose names she will never learn, in laboratories and maternity wards and prison infirmaries she will never see. This is how medical progress works, not with a single moment of revelation, not with a flash of genius that illuminates the darkness all at once, but through a slow, grinding accumulation of knowledge extracted from failure, from grief, from the bodies of the dead and the blood of the living. The triumphs arrive quietly. They become routine. They settle into the background of ordinary life, as unremarkable as clean water or electric light. Miracles so thoroughly integrated into daily existence that they cease to register as miracles at all. The shot at 28 weeks. The typing card in the medical file. The small vial of anti-D immunoglobulin that contains, in its few milliliters of clear liquid, the distilled product of 60 years of human ingenuity and human cost. But beneath that routine, beneath the clinical calm and the bureaucratic efficiency, something remains unresolved. Not the medical question. That has been answered, at least for the populations wealthy enough to afford the answer. Not the logistical question that is being addressed, however slowly, by international health programs working to extend anti-D access to the developing world. The unresolved thing is older than medicine, older than science, older perhaps than language itself. It is the question of what it means to carry in your body a trait that should not, by the cold arithmetic of natural selection, exist. 15% of European humanity carries a deletion where a protein should be. A protein conserved for 160 million years, shared by every primate species on the planet, erased from the human genome in a single event sometime during the last ice age. That deletion created a blood type that, for most of human history, functioned as a silent mechanism of infant death. A molecular incompatibility between mother and child that destroyed pregnancies with the precision of an immune response, doing exactly what it was designed to do. The disease it caused was invisible for millennia, misattributed for centuries, partially understood for decades, and finally prevented, not cured, not eliminated, but prevented, through a pharmaceutical product derived from deliberately sensitized human blood. The story is complete in its arc: problem, investigation, solution, tragedy, understanding, prevention. It satisfies the narrative hunger of a species that organizes experience into stories with beginnings, middles, and ends. But the satisfaction is premature because the deepest layer of the story, the why, remains untouched. Why does Ra-negative blood exist? Not how. The how is known. A deletion on chromosome 1, recessive inheritance, population genetics. But why did evolution permit it? Why did it persist? Why does it cluster in specific populations? Why did certain cultures build elaborate systems of bloodline preservation around traits that may or may not correlate with Rh status? These questions do not have answers. They have hypotheses, and hypotheses not answers. They are scaffolding erected around the shape of an answer that has not yet arrived. Perhaps the answer, when it comes, will be mundane. A genetic hitchhiker carried along by a nearby beneficial variant. A founder effect preserved by geographic isolation and reinforced by cultural endogamy. A neutral trait that drifted to moderate frequency through the stochastic noise of small population dynamics. These explanations are scientifically respectable. They're consistent with the data. They may well be correct. And if they are, the Ra-negative mystery dissolves into ordinary biology, a footnote in the vast catalogue of human genetic variation, no more meaningful than the distribution of earwax types or the ability to taste certain bitter compounds. But perhaps the answer will be something else. Perhaps deeper investigation will reveal a selective advantage so subtle it has escaped detection for decades. A physiological difference that mattered profoundly in ancestral environments, but is invisible in modern clinical settings. Perhaps ancient DNA will reveal patterns of admixture between Homo sapiens and archaic human populations that reshape the Rh system in ways we do not yet understand. Perhaps the cultural dimension, the persistent, cross-civilizational obsession with blood purity, sacred lineage, and divine descent, will prove to be not merely a metaphorical response to social hierarchy, but a distorted memory of genuine biological distinctions that ancient peoples observed and encoded in their myths. Or perhaps none of these things. Perhaps the Rh mystery will remain partially open, one of those questions that science can narrow but never fully close, where the data are sufficient to eliminate the impossible but insufficient to confirm the true. Not every question has a clean answer. Not every mystery yields to investigation. Some remain suspended, held in the space between evidence and interpretation, between fact and meaning, between what the blood carries and what the mind makes of it. What is certain is this. For thousands of years, a molecular incompatibility killed children in silence. Mothers buried infants they could not save and carried guilt they did not deserve. The cause was circulating in their own blood, and no one, not the mothers, not the midwives, not the priests, not the physicians, had the language or the tools to see it. When the tools finally arrived, they arrived piecemeal, over decades, through a chain of discoveries that stretched from Vienna to New York to Liverpool to Auckland, each link forged by individuals who saw a piece of the puzzle and refused to look away. The solution that emerged, a simple injection, given twice during a pregnancy, stands as one of the most effective preventive interventions in the history of medicine. It has saved millions of lives. It continues to save them every day in every clinic where it is available. And in the clinics where it is not available, the old pattern continues, quietly, invisibly, in the spaces between funding cycles and supply chains and political priorities. The blood that kills its own has not stopped flowing. It has merely been diverted, channeled away from the populations that solved the problem and left to run its ancient course through the populations that have not. Tonight, somewhere, a woman receives an injection she does not fully understand, and a child she has not yet met is saved by the accumulated knowledge of a century of grief and genius. She will not think about the blood. She will not wonder about the protein or the deletion or the 160 million-year-old molecule that her body lacks and her baby carries. She will think about names, about nursery colours, about the small, ordinary future she is building for a child whose existence was made possible by strangers, by a pathologist in Vienna who died at his bench, by a mother in Chicago who buried 3 children and then wrote a paper, by prisoners who offered their veins, by a man who gave his blood 1,100 times, by midwives and researchers and donors and dreamers and the countless unnamed women who lost children before anyone could tell them why. The blood remembers what the world has chosen to forget. And somewhere in the silence between heartbeats, between the cells that carry the antigen and the cells that do not, between the mothers who were saved and the mothers who were not, the oldest question still lingers. Unanswered, unhurried, patient as a protein waiting on the surface of a cell for the immune system to decide whether it belongs. Some absences define us more than any presence ever could. The missing protein, the missing children, the missing answers. They're all part of the same silence, the silence that began before language, before medicine, before anyone thought to ask what blood was made of and why it mattered. That silence has not been broken. It has only been made louder by everything we've learned and everything we still do not know. The blood flows, the question remains, and the night as always keeps its secrets.